Do you need to? It's not.
Yeah,
Okay.
he's helping, but he's not.
Thank you. Thank you. We also need help with the screen because,
He's,
like,
yeah, but the gentleman, he's actually the stream. He does the streaming to YouTube.
Right,
He was just helping.
okay, it works
He
now.
must have clicked on something.
It works now. Excellent. I have a microphone too, so I guess it's pocket and clip.
Take off your there so it doesn't bang you.
Absolutely.
And we normally have you run it down your shirt, but it's up to you. You can just click it on if you don't mind having the string, the cord there.
It's gonna make a lot of noise. Can I mute it? Yeah. Either way.
That's fine.
Okay.
If you want to.
Cool. Thanks. Okay. I think we're ready to get started. Thanks for coming, everybody. Sorry for the delay there. It's early. Everyone's waking up. My name is Sam Friedman. I lead firmware engineering for Goliath. Goliath is a cloud device management platform for embedded devices. We work on Zephyr, which is why we're here. We also work on a couple of other platforms. My talk today, though, isn't about Goliath. It's about microservices for microcontrollers, composable software architecture for embedded systems. Also, I wanted to mention this is my first conference talk ever, so thank you for being here for this momentous occasion for me. All right, so if you've heard of microservices, you probably are wondering, like, isn't that a cloud thing? Why are we talking about them at an embedded conference? And it's true that as microservices, the term is like mostly known, it's a cloud thing, and it's also true that I chose that term to make my talk sound a little bit more interesting, but what we're really talking about here are just really modular software. In the cloud world, microservices are like very small individual pieces that can be deployed very quickly and very independently, and it's designed so that really large teams, like the big companies, don't need to coordinate thousands of engineers to release their web app every time they need to release it. They can release small pieces of it all the time. That's not usually a problem for firmware. You have to update the whole firmware all the time anyway, and our teams tend to be smaller. But we can still gain a lot of the benefits from, or a lot of benefits from using a sort of microservices-like architecture. What it looks like in firmware is, again, just very small, very loosely coupled, independent tasks. We'll talk more about what a task is. Communicating through well-defined IPC mechanisms. And so the analog there would be like, through a lightweight API. In the cloud world, we're just using IPC here in firmware. The benefits you get from that are similar to the cloud world. You can move faster because smaller things are easier to test. They're easier to understand. Things that are easier to understand, they're easier to maintain. And they're more isolated. So if you need to make a change into one part of your firmware, you're less likely to have that impact the rest of your firmware. That's just good software architecture, software practice, I think, for any software that you write. But the part that I want to stress is actually composability, and we're going to talk about that more here just in a minute. This is really why I think this architecture shines for firmware. So what is composability, right? You can think of it basically, you have a bunch of Lego bricks, a bunch of small pieces that you can assemble to create something bigger. Just like with Lego, if you have just a very simple brick, you can combine them to create very complex, very beautiful things, right? It's the same way of thinking of that for your firmware, right? You want to break things down to the smallest pieces so that you can pick and choose them. The reason they need to be small is that having smaller pieces makes them more reusable. If they only do one thing, then you can pick it up and use it. You don't have to worry about, is this going to bring in a feature I don't need? Is it going to have a dependency on a piece of hardware that I don't have because it's trying to do too many things? This little guy in the corner, we call him Echo. He's pointing right here because this is why that's really important for firmware. In the cloud world, when you deploy your new web app, the old version is basically gone, right? It's deleted. No one's ever going to use it again. All of us who make embedded devices know that's not how firmware works, right? Once you deliver a product into the field, that product needs to be supported until it's no longer being used, right? Even if you can update the firmware, your users may not choose to update it. And as you release new hardware versions, right, adding hardware, changing hardware, removing hardware, adding features, removing features, you still need to support the old versions of your product. Having composability allows you to use the same code, because what you're doing now, instead of rewriting your firmware, which I've been part of a lot of teams who have changed one little thing in their hardware and rewrote the entire code base from scratch, instead of doing that, you're now just adding a piece, adding a software module, adding a task, removing a task. The configurability of it, the composability, is what allows you to reuse your code faster, better, while also getting all of the other benefits that we talked about earlier, including better testability and maintainability. All right, so what does that actually look like? We talked about tasks a little bit earlier. Tasks are these independent actors in a system. They need to communicate through IPC. One thing that I mentioned is lots and lots of small tasks, which if it might have made some of you think, like, well, I don't have memory for like 1,000 threads running. So we'll also talk a little bit about event tasks, which are a way of having really small pieces of independent software functionality, but without using up all the resources of like a heavyweight thread for them. So tasks. Like I said, they are fine-grained, many, many small tasks. You want your tasks to be as simple as possible. They should really just do one thing. And you should think about them as I'm calling them business functions here, but essentially either a feature or hardware support to do one of those things. And they should be loosely coupled, which is something you've all heard before. The way I like to define it is no public interface. So there are no header files for tasks. You cannot call into them. They have no APIs at all. Instead, all communication is through IPC, through indirect IPC. So this means they're not exposing a queue that you put things into, but instead there's some other inter-process mechanism that allows these threads to communicate with each other without actually knowing with whom they're communicating with. And we'll get into that in a minute. And then these tasks, because in order to ensure that they can be added and removed at will, they all need to sort of be on the same footing, right? You can't have a main task which is trying to coordinate those tasks, because then you'll have to change your main task every time you add or remove a task. Doing hardware initialization in the task itself becomes difficult, because if you have 3 tasks that are using the same driver and one of them sets it up, but then that's the one that you want to remove, now you have to figure out where else to initialize that driver. So I guess these are a lot of like prohibitions, which I think is maybe the main takeaway from how to think about this. It's how do we keep everything really self-contained? How do we keep everything as concerned with its one function as possible, so that when that function is no longer needed, we can remove the entire software component? Or similarly, when we add a new software component, because it's only concerned with its one function, we don't really need to make changes or the minimal set of changes to the rest of the firmware. And as I mentioned, tasks, we have those event tasks as well. So all threads are tasks, but not all tasks are threads. For IPC, there are a couple different ways that you could do this. I prefer PubSub, and this is not like a product, so I've capitalized it. This is just generally a communication paradigm that you can think about. I'm sure many of you are familiar with the basic concept, but you have topics and devices published to them, tasks published to them. Tasks can subscribe to them and receive messages. The important thing about it is that the focus here is on identifying that data, so naming the topic like accelerometer, or temperature, or GPS, or whatever. Sensor data is like the easiest one to think about, so it's probably going to over-index on that. And what the form of that data is, rather than on how modules are interconnected. there's going to be more concrete examples later, I promise. Right now, it's a lot of talking. And that's the important thing, right? So modules are communicating without knowing what the other party is. And that's important because now you can remove, change that party, add a new one without needing it. It's also important to note that this is many-to-many, and that's also important for like when you want to add a new feature that can like hook into an existing data stream, right? Like that's just naturally supported. This removes the inter-task dependency. So we mentioned that there's no public API. The reason why that's important, right, is again, because like if you stop compiling in a function that another module is calling, then that you're going to fail to link. So these tasks don't communicate with each other. Their dependency is on pub/sub. So pub/sub has to be there. Whatever your pub/sub bus is, needs to be there in the system. But that's pretty much the only direct dependency for the system. Another advantage of this, and again, I want to stress that like for me, the main point of this is composability and being able to support multiple firmware products with one set of code. But there are a lot of other benefits too. One of them is removing developer dependencies, development dependencies. So if you are developing a module that communicates to and from pub/sub, right, this kind of gives you a built-in abstraction barrier where you can easily inspect or inject data in order to test the module before the rest of the whole software is ready. And what's great is not just doing that when you are in development, but in testing later too, because these injection points basically don't go away. They're part of the actual core system. You can use them throughout the life of the product. So where I've used this in the past is like if you have any kind of UI on your device and that UI is triggered based off of events, those events are pub/sub messages. Triggering your screen is really easy. You have a little CLI command that can just like fire off a pub/sub message and trigger any screen you need, any animations, things like that. Similarly with pulling off data, you can just write a really simple application that just like opens up the accelerometer topic, reads it, prints it, and that becomes really easy to interact with. And then finally, the last task we were talking about are events. I think there's another corollary to the cloud here, which is cloud serverless functions are pretty similar. So I'm calling them threadless functions. It's multiple tasks. They run on one thread. These are essentially callbacks that execute in response to a pub/sub message. So you register them against a particular message. They run on a shared thread. So they run to completion, right? And it's important to note that they are not tasks. So you need to be careful. Think about them maybe not quite as, as performant as interrupts need to be, but kind of in that vein, right? They can't block for a very long time, right? Any sort of operation like that is going to prevent other events from running. And so actually, this is probably a good point to talk about, like, how do you choose what is an event or a thread? Generally, anything that needs to like directly interact or wait on hardware is going to have to be a thread. Like most flash writes are going to, they can take a long time, so you don't want to do those network operations. Even some sensors you need to read from, in maybe like a polling manner, if there's any kind of delays in there, tend to be threads. And then more like pure business logic tend to be events. And again, these events, things you would use for events, are probably not things that would have been their own thread or their own task in like a traditional system that you might have built before, because we're trying to really create a lot more tasks than you would normally see in order to create the small little Lego blocks and keep everything composable. And again, concrete examples coming. All right, this is the Zephyr Developer Summit. So how do we do this in Zephyr? ZBus is, I think, still relatively new, maybe about a year old. It's really great. This is Zephyr's implementation of a pub/sub bus. The terminology that they use is a little bit different than what I was using before. Topics are channels. Messages can have data associated with them, which is great. The threads, so you can have what they call thread subscribers, which are the thread tasks that we talked about. It's not shown here. They can actually have a couple of different kind of messages. You can either like receive a copy of the actual message into your own queue, or you can receive a reference to a message. As far as like the architecture part of this, it's not really so important. They also implement what they call listeners, which is what I was calling events earlier. So that's really nice. You don't have to implement your own event thread or anything like that. That's already built into ZBus. And this takes a lot of the work and complexity for you. I highly encourage you to go listen to the Zephyr Tech Talk on ZBus. I think it was actually phrased or like positioned as kind of like a debate, like should you use ZBus, should you not use ZBus? All the Zephyr Tech Talks are great. This one's particularly relevant for this talk. The next thing is iterable sections. This is maybe a little bit like non-obvious about how important this is. I mentioned before that there's no public interface and there's no main thread coordinating which tasks are running, right? So how do these tasks actually get put into the system? Essentially, including a task is the same thing as compiling it, right? If you compile a task, then it gets into your build and it will run. The way that works is using iterable sections in Zephyr. What this is basically you place a struct into a particular linker section at build time, and then the linker grabs everything from that build section and puts them packed into, into an order. And that essentially creates an array in Flash, and then Zephyr has facilities to like iterate through that. What this means is you can create, basically modules can register themselves. They can place themselves into global arrays without there having to be any kind of like central registry in your source code. Just by compiling it, the linker ensures that that's placed there. So Zephyr uses this for registering channels for ZBus, for registering the listener events. It uses it for task or for thread creation. Again, the importance of this, right, is that it prevents you from having that central piece of code that is orchestrating everything that you need to change every time that you want to create a new version of your firmware. Instead, all you do is you set a kconfig option or maybe change something in your CMake file to include or exclude a component, and that becomes the entire like building of the application, right? And then the last part of it is system initialization. So this also uses iterable sections, but I mentioned before, you can't rely on any task to do the initialization because you may remove that task. Zephyr has a really robust initialization system, which a lot of different levels. One of the things where in other systems, actually, this can get pretty hard is if you don't have a main task to ensure that you initialize things in the right order. Maybe your display needs the power regulator initialized first, things like that. If you're just kind of relying on which threads run or it can be pretty difficult. Zephyr has initialization levels. They have initialization priorities within levels. All of this, again, done through those iterable section structs that get placed in the linker. And this allows you to pretty fully specify the initialization order and what hardware and libraries need to be initialized in those libraries and drivers themselves. So your application doesn't need to do it. So by the time all of your tasks run, they're all ready to run, and they're all able to leverage the full capabilities of your system. And again, this is important because if you remove a task or if you add a task, you could be changing your initialization, which could cause complexities when you're building the various products on your one code base. OK, real-world example. That was a lot of talking, and I apologize. It's not how I like to do my presentations normally. But hopefully this will make everything feel a little bit more concrete. I want to talk about a cold chain asset tracker. This is actually a cold chain. This happens to be a reference design that my company Goliath makes, but I mostly chose that because I know there are no copyright issues with this photo, so it's not important that my company makes it. What this is it's a little GPS device with a temperature sensor and a cellular modem, and you put it in your frozen food shipment, in the back of a refrigerated truck, and it ensures that throughout the process or throughout the shipping of your food, it never goes above freezing, so it hasn't spoiled, right? So this is a little block diagram here on the right side of that screen. The sort of rounded rectangles are tasks, and the diamonds are pub subtopics or ZBus channels. This is obviously simplified. There would be a lot more going on in the system normally, but for the purposes of this, I think this is a good example. So the GPS thread, these are actually all 4 of these tasks right here are threads in this contrived example, because I mentioned, right, like if you're dealing with hardware, you're generally going to need a thread, something that can block. So the GPS task is publishing to the position topic. The sensors task is publishing to the temperature topic. Both are being consumed by the network thread. That's one of the simplified things. That would probably be a couple of different tasks. But both are being consumed by the network task in order to upload that data to some cloud database where you are tracking this, or maybe a visualization tool. And then also to display, so we can display that data locally. So that's sort of the base, but let's say your product manager comes back to you. They say, hey, we talked to the customer. They're tired of the drivers in the front. They're not looking at the screen. They have no idea when the temperature rises. We want to add a new feature that plays an alarm whenever the temperature rises above a set limit. So we can add a new task. This task is actually going to be an event task, or again, a listener in the ZBus nomenclature. What this task does is it just runs every time there's a temperature message, and it compares that to some threshold, right? And if it passes that threshold, then it publishes a message to the overtemp topic. So I just described to you the entire task, right? You can imagine that's probably like 4 lines long. Just to emphasize that tasks should be really, really small. That is a feature. That's a piece of functionality. That's all it should be. It's in its own C file. It has no public API. It's just that one function. But it is a task because it is that independent piece of functionality, and it's not going to take any extra resources on your system because it's going to run on that event processor thread. So it publishes to the overtemp topic, and then that overtemp topic is something I should have mentioned about this. So the arrows that show the data going, position pushing data to network, it's sort of describing the flow of data, but remember that these tasks subscribe to that data. So they're actually calling into ZBus or your pub subsystem to say, hey, I'm interested in position data, right? So the display, we do have to change the display a little bit because we are changing the display. We're adding a new screen. So we have it register onto the overtemp topic. And we create a new screen that puts up maybe one of those little warning symbols. We also add a new audio task, which maybe plays a tone or a buzzer or something to audibly alert the driver. So that's great. That's our new thread. We had to change the display a little bit, but we changed it because we actually are changing it, not because it needed to be changed in order to support some other change, right? The sensor thread is now sending data to the alarm task, but we didn't have to change anything in the sensor task. We didn't change a single line of code there. So that's kind of where this architecture shows its value. But I think it's even better when you delete something. So let's say, the product manager comes back and they say, hey, these are really expensive. We don't need a display. The driver's in the front. He can't read it. Why do we need a display? Let's delete it. Let's save some money. That's it. You delete it. You just delete the display task, and the rest of your firmware will still run. All these topics are no longer subscribed to by the display task, so they're no longer getting data. You no longer have to. So yeah, it's not running anymore. I actually spent quite a while trying to see if there was more to talk to on this slide, but I think that's kind of the point, right? Is once you've separated everything into these very distinct pieces of functionality, and once you've ensured that they are loosely coupled, you can remove things and it doesn't affect anything else, right? I've had the experience in the past of trying to remove a screen, like a piece of the UI, and when I hit build, the file system recompiled. So somewhere there's some weird dependency where the file system is depending on the screen. I never figured out what that dependency was. But when you build it up like this and through this system, that doesn't happen anymore. So that was it. Pretty quick. We have about, I think, 10 minutes left. Are there any questions? Yes, I don't know if we have a microphone in the mic.
Hi, thank you for the talk. Just a question on how would you manage like dependency initialization, especially if you have to initialize services at different times?
Sorry, could you repeat the first part of the question?
Yeah, how would you manage initialization priority?
Mm-hmm.
So for example, if the task you want to implement has several dependencies, right?
Yeah.
And you're not very sure when these dependencies will finish initializing.
Yeah, that's a really good question. So Zephyr actually has built-in support for this. There are different initialization levels. I'm not gonna get them all off the top of my head, but there are several different levels that you can do before the kernel boots, several after the kernel boots, some at what they call the application level. And then within that level, there's also, you can set a numerical priority, which I think is 0 to 99, or some other quite large range where if you need more than that, you're probably building a very complex system. And so you set those initialization priorities according to your system. A lot of them, may not be in code you can necessarily control. There might be modules that are in the Zephyr tree itself. A lot of those have kconfig options that you can set in order to change the priority if you need to.
Thank you.
Hey, great talk. Food for thought, did you think about mixing the system with linkable, loadable extensions so you could even just have a small piece you can push through the system or small functionality?
Yeah. In relation to this kind of architecture, I haven't thought about it till right now. I think that's actually a really great question because this can kind of enable that, right? Because it sort of, once you load that module, it can subscribe to these topics, and that doesn't necessarily need to happen at build time, right? So yeah, I think that provides, I guess, yeah, I think those work really well together. You'd have to be careful to when you unload a module to make sure that you unsubscribe from all the channels that it was connected to. But that's more of an implementation detail.
You may not know the answer, but performance of ZBus. For example, the products I'm re-architecting right now, we deal with sometimes, say, 6,000 messages per second going out of the device. And so we have to do all of the work to gather the data and collect it, so we're dealing with a higher rate than that internally. Do you think ZBus can keep up with that?
Well, I won't give you a definitive answer because I don't know how fast your processor is and things like that. I will say that there is some overhead. It's pretty small. So I mentioned briefly that there are two kinds of ways you can subscribe to ZBus. And one is where ZBus will copy messages into your queue, and another one where it passes it by reference. I imagine if you're sending around 6,000, you're probably doing it by reference, so that is pretty performant. I've implemented a pub-sub architecture in the past where we used strings to describe the topic. So you had to do some string compares, which aren't the fastest and not too slow, but ZBus doesn't use that. They're using integer channel IDs that are defined at compile time through the linker, so that's pretty fast. So essentially, the other thing that I would say, and actually I'm not sure exactly how ZBus is implemented here, so take that with a caveat. The way I've implemented systems like this in the past is using linked lists. So if you have the performance there grows with the number of topics and number of subscribers you have. So if it's a high volume of messages going between a small number of tasks, that probably is not an issue. But if you have 6,000 tasks, then sending a message could take iterating through 6,000 subscribers. And again, I don't know how ZBus is implemented. Obviously, there are ways you could speed that up, sorts and searches and stuff.
So the reusable logic part is great. I'm wondering how, with the iterable sections part, how that sort of handles reusing the same task. So say you had 3 temperature sensors and you've got a task which reads the temperature sensor and pushes it somewhere. If it's all sitting in the one C file, that doesn't, like, you can't create that 3 times, for example.
Right. So most of the entries in the iterable section have like a name. Or so basically the way this works is there's like a macro. One of the arguments of the macro is a name. So you could actually like instantiate that struct that describes that task multiple times. You would, it would be like temp sensor 1, temp sensor 2, temp sensor 3, but they would all have the same, they would all use the same function. So you could at least reuse that function call. And then most of these iterable sections also take like a context argument, right? Like a user void star, right? And so you could pass the context in there to say like, hey, you're actually reading from, this temperature sensor, that temperature sensor.
That's one big room.
Hi, yes, I'm very new to Zephyr, so I don't know all of its capabilities. I was curious about your architecture concepts in relation to possibly multi-core usage. Is that of a play there, or?
That is a great question that I do not have the answer to.
Fair enough. But you wouldn't knock it out of the part. You wouldn't say it's a no or something like that.
Correct. I wouldn't. Most like inter-core IPC mechanisms kind of work with like a hardware mailbox anyway. So sure. I could definitely see extending ZBus to like use that as sort of like a backend.
Right.
But I've never like.
Gotcha.
Honestly, I've never really worked with like a SMP very much myself, right? When I've used 2 cores, it's been like this core does a very specific thing. So.
Gotcha, yeah. I work in SOCs all the time, so it's always how do you get them to work together? So
yeah.
It's interesting. Okay, thank you.
Thank you. Hello. Thank you for your presentation. If I understand well the pub sub, you have a module or a task that is the publisher and another one that subscribes to it. So every time a publisher publishes something, the subscriber will be notified and do something with that information. But sometimes the subscriber doesn't want to be notified, or the subscriber wants to get the information when it's needed. For example, the over temperature alarm that you mentioned. That could be a situation where, oh, there's an over temperature. I want to know the position where it happened. So I'm interested in a position now. I don't want to be getting events all the time a new position is published. So does ZBus support that as well?
That's a really good question. That was some slides that I took out of the presentation, actually. I don't believe ZBus supports it, and I'm actually not aware of like a built-in library in Zephyr that does it, although anyone, please feel free to correct me. But what I usually refer to that is shared state, essentially, is what you're asking for there. And you can do something similar where you create a central module that can like hold shared state, and where you basically, it's similar to ZBus, you refer to that state by like an ID. So you're like calling into this module and you're saying like, hey, give me the, the current state of this identifier, rather than like directly accessing the memory itself. There are a couple advantages of that. One is that this system can know whether or not that data exists or not, and that's important for like, let's say, you remove the task that sets location, right? You just care about the temperature, you're not doing position anymore. Well, you don't want to just, display junk data, right? You need a way to say, well, there is no position information, actually. The other thing is that it allows you to abstract away concurrency protections. So you can do all of the concurrency protections, mutexes, whatever kind of lock you're using within that module. So you don't need that in all of the tasks, which in my experience, some of the hardest bugs to track down are around concurrency. So if you can reduce the surface area of where those bugs can pop up, that's really helpful.
Thank you very much.
Hi, I actually have a follow-up on that question. What that sounded like was an RPC between two modules with a command and response. And I'm wondering, you mentioned not defining APIs for these modules, but typically a function like API surface is a great way to define an RPC. Can you speak to that trade-off of not defining an API for this, or how you go about that?
Yeah. So I will say, to be clear, I was not trying to describe an RPC before. More of like a file system, which I hesitate to say because it's not really anything at all like a file system, but saying like, give me the contents of, foo.txt, right? More like that. For an RPC, I think you could do it. Like RPCs can be decoupled. You generally still need to know sort of like who you're sending that request to, which can create a little bit more of a tight coupling. It's certainly less than if you're doing like a function call, right? And also, I think there's benefit in thinking of like the data flow, right, rather than like the execution flow of a function or of a program. And this gets into things like inversion of control, right, where it's like rather than like asking something to happen, you just say that like this thing exists and wait for somebody else who cares about it or not. So it's certainly, I would say RPCs are possible for sure. I'm not sure that like in an embedded system though, where you can link everything together anyway, that there's as much benefit from it as you get in like a cloud system where the main benefit from RPC is being able to like pretend that something very far away is actually very close to you.
I think we're slowly running out of time, so perhaps one more question and that's it. And I also looked the Discord if we have any questions there.
Thanks. Yeah, we've implemented something sort of similar in an architecture with that, and we use sort of shared states to sort of share between different things. But my question was about the, I guess the channels. Is there a way that a channel can know when you're publishing to a channel, you can actually know how many subscribers you've got? Because if you've got dynamic tasks that are being switched off, suddenly you don't need the temperature or the accelerometer data anymore. It'd be great to be able to have that sort of publisher to be able to go, okay, well, no one's subscribed to me, so I'm just going to go down into low power mode and wait until somebody subscribes again. Does Zephyr channels allow for the publisher to know how many subscribers it has?
That's a really great question, and I agree that'd be a really useful feature, but I don't know the answer. Sorry.
Okay, right. Thanks.
All right, so I think formally that's the end of the session, but of course I assume that you might have more questions. You can just ask them privately. I think we've had a little break now before the next talk, so if you could just thank the speaker.
Great. Thank you all. Yes, I'll be out here for a little bit, and then you can find me in the solutions showcase at the Goliath table for today and tomorrow.
And 9:55 is when the next talk starts.
1, 2.
So there is another speaker. I'm not the speaker, but there is Chris. That is
Yeah,
somewhere.
he should be here, I
So
suppose.
we need
But
another mic. Yeah.
okay.
I'll try to find Chris.
Okay. Seems that it works. Yeah. Yeah. Okay. Cool. Okay. Cool.
Check, 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 check. Check, 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 check. Ready to go.
Beauty.
I've
Thanks.
already got it unmuted.
All right.
I'll be back there to adjust your levels.
Okay.
There is a handheld mic available for Q&A. I don't know if you'll need a second one, but
15 minutes is too much.
How's it going, May?
Hi. How are you?
Good. How are you?
Yeah. That's cool.
You ready?
And I can hear myself. That's,
Always ready.
So that's fine. Yeah.
put the timer on.
Wake up
Okay.
ready. I'm gonna move this.
Okay. Makes sense. Yeah. I will start with a timer.
I'm just gonna move this so it's not right under my chin. That's okay. So it's not helping with our phone controllers, by the way. Awesome. Is this gonna like interfere?
I don't know. No. Is it on?
I think it's definitely on.
1, 2, 3. 1, 2, 3.
Yeah, can you do that for me? Just like maybe off the side of it. I've got like this beard going on, so it's just kind of like.
You're like very West Coast, eh? Because everyone on the West Coast has a beard. Like everybody from At Micro has a beard, so.
Except Peter.
Yeah.
He doesn't. Yeah.
Oh, that's true.
Yeah.
Okay. Earl, yeah.
We have our bottles.
Swag.
Yeah.
It's important. Oh, did I give you? I gave you stickers, right?
Yes.
Okay. I have to get rid of the rest of these before I go back.
Probably even leave them somewhere. People will just grab them.
I think I might at some point towards the end of our talk, I'll be like, "Oh yeah, at 10 Store, come talk to us. We're hiring or something like that."
There is a timer there. We'll have it started up.
That's very useful, by the way. It's like every single talk should have that, because I talk, it feels for me as if it was 15 minutes, and it turns out it was an hour, so it's horrible. I'm very bad at it.
Yeah.
This is really
My tongue wash. Turn this off.
Hello everyone, I think our time has come. The next session is about to start. Well, we might wait like 30 more seconds, but after that, I'll leave the floor to Carol and Chris and let them introduce themselves, I guess. Yeah, if you have questions, we'll ask them at the end of the session. I'll bring the microphone to you. So without further ado, go ahead.
Thanks. So my name is Karol. I'm from OnMicro, and I'm here with Chris from TenStorrent. And today we'll talk about library we developed for easing development of PCIe-based devices and for testing the software that runs on those PCIe devices. So why do we even care about that? So if you look at what's happening nowadays, more and more companies develop their own offloading accelerators. Yeah? You cannot really calculate all the stuff and process all the data that we want to process nowadays on our general purpose CPUs. So you have to offload some of those tasks to some additional dedicated hardware. And since the amount of data that we need to process is huge, we need like pretty fast interconnects and pretty fast interfaces for those accelerators. So PCIe is an obvious choice. It's like well-known, commonly supported across many platforms, and so on and so on. A great example of such accelerator is what actually Meta showed last EOSS, last Zephyr Development Summit in Prague. In their keynote, they develop a custom silicon for codecs and AI accelerator. There is also, the second example is what Instorance right now does. There's again a PCIe-based chip that can be used as accelerator. So this is obviously something that we will have more and more of those. So if you know, if you don't, you'll hear about it in a moment. All those pieces of the system, they do run software. I mean, you have a software on the host side, that's obvious, but you have a bunch of software running on the devices. So the devices are not purely in silicon. They have CPUs. They have a bunch of software or firmware that is running there. And of course, you don't do a waterfall development because we don't have time for that. The hardware team is working on the silicon, while the software team at the same time is working on the software. And since there's no silicon, you need to have some kind of a possibility of running the software before the silicon is ready. So you need some kind of an emulation. And it would be perfect if the emulation can actually simulate the exact PCIe infrastructure and the exact PCIe communication.
Testing, of course, right? We want to test everything continuously. So
yeah, exactly. So even when the silicon is ready, you need to have a simulation for that. So how we can do that? Yeah. So basically, testing of such systems is pretty complex because you need to have a host part, you need to have a device part, and they do have to communicate. So you need to run, while the host part can somehow be run natively, the device part will pretty always be a different architecture or a smaller CPU, smaller SoC. So you have to somehow simulate that embedded system actually that is there on the device. And of course, you need to somehow communicate them. You need to somehow create this virtual bus connection, exchange the data back and forth. And the more you can test, the more you can cover, the better, because you will just avoid problems in future. So how can you run this simulation? So the obvious choice for, especially if you are an ASIC developer, like RTO developer, is just to run simulation of the whole system, like RTO simulation. It's pretty accurate, like clock cycle accurate. And will tell you everything. Like if something works there is a big chance that it will work on the hardware. Of course, if the rest of the physics is okay, because it will simulate the digital part of the whole system. But unfortunately, it is slow. I mean,
cycle accurate, right?
Yeah, I mean, it comes at a price. It's super accurate, but clock cycle accurate. But you have to take into consideration every single event that is happening in a digital system, very complex digital system, to do that. There are, things like simulators like Verilator, which is a fast one, but still, considering the complexity of the system, it will take time to run a simulation of that and boot software and actually test it. And software developers are lazy or maybe not lazy, they require immediate response or immediate answer. You run make and you need, if the result is not there after 10 seconds, you just go for a coffee and you forget what you did. So we need it fast. So we can switch to something like something that is called co-simulation, where part of the system is actually simulated still at the clock cycle level accuracy, but the rest of the system, majority of the system, is typically simulated at the instruction level. Yeah, so for example, you simulate a CPU and a bunch of peripherals at the instruction level, where you don't care about the exact timings, the exact like physics of the system, but you do provide the information that software needs for that.
Yeah, so I mean, I guess the big difference is, functionally accurate versus clock cycle accurate. So when you're bringing up brand new hardware, you want that cycle accuracy, but for the faster stuff that you're already you have confidence in, like the host system, the functional accuracy is fine. Mm-hmm. How many people in the audience have done like hardware emulation of new systems? Anybody? Okay, so let me ask you a simple question. Like, let's consider 3 scenarios. What's faster? Or what's faster and what's least painful, I suppose, is a good question. So hardware emulation, sitting down there with your emulator in the system and, reloading that image in the bit stream over and over again, versus writing a model, a machine model in QEMU, versus composing your hardware dynamically and then using an emulated bus. Anyone want to guess? Anyone? Option C? That's correct.
Yeah, exactly. So that one will just give you something that you can work with way faster. And in the end, since the half of the system, like bigger part of the system, actually will be just like instruction level, not really cycle accurate, it should work faster. However, still, if you want to simulate PCIe, the whole serialization, deserialization part, clocking can be pretty complex. So the RTO level simulation will still slow down the whole experience. It will be faster than just pure RTO, but still not what we want when we develop software, because we want answers immediately. So why not switch completely to instruction set simulator and just have everything as fast as possible? Of course, it's doable, and there are some models of PCIe devices that you can use. The biggest problem with that they are not really modeling the real underlying hardware, because they typically default to things like you do the initialization and then you leverage the fact that PCIe devices are simply memory mapped. So every single transaction to these PCIe devices is in those ISS simulators is immediate. You don't have any delay. You don't have any possibility of injecting any errors or modifying the transaction, or even figuring out what would happen if I have to wait for my transaction. So you may not catch any problems like there is a physics underneath, and everything goes fine unless I have to wait for the data. So that's not something that we want to use. Of course, it is used widely, but we still would like to have a better representation of the hardware, but without the overhead of simulating that on the clock accurate or cycle accurate level. So here comes Warpipe, a library we've been working on. So Warpipe is a collaboration between Antmicro and Meta. We did that together to actually build a piece of software that allows you to construct bigger complex systems where you can still be in the instruction set simulator speed grade, but model the underlying hardware infrastructure and somehow model the fact that PCIe transactions are by nature packetized, and there is a stream of data, not immediate data appearance on the other side. It's fully open source, licensed on Apache license, written in C. You can just go to this link and grab it, run the tests, integrate with the system, and to do whatever you want with it. So it's there. The idea behind it is that it's OS agnostic. We don't really. It's not implemented in a way that you have to, use it with Linux, Zephyr, or whatsoever. However, there are some helpful features that we'll be talking about in a few slides that they are ready to use with Linux and Zephyr. So that's that.
And of course, we're capitalizing on the fact that PCI Express is a networked architecture. It's no longer like a simple bus. We have a network, and there are components in the network, and it's packetized. So.
So if you look at the schematic, I think you wanted to talk about that?
For sure. This is kind of the key feature, I would say. So what we have is we have the physical layer, we have a data link layer, and so on and so forth. Warpipe just sits in the middle. We're basically emulating things at from the almost the application layer all the way down. And what we're doing is DLLP representation and TLP representation. So that's data link layer and transaction layer.
And the library, of course, comes with a bunch of like helper functions that allow you to like integrate that kind of a system. And in its core, it's at the very bottom, as you can see, there is this nice pipe there. At its very core, it actually handles the transactions there. So in Unix, we use, in Linux, basically, we use Unix sockets to transfer the data back and forth. So what you get from the libraries, beside, of course, the core functionality of handling the communication and connecting two different pieces of the simulation, you get the whole logic for that helps you implementing the whole stack of the PCIe flow. So basically, logic for packetizing, depacketizing, the transactions. So it's super easy later to implement a model of a PCIe controller in your hardware. Things like some helpers that allow you to simply describe a PCIe device with a YAML file, like human readable format, and then it would convert that immediately, like on the fly, to this descriptor, like PCIe device descriptor that then can be read from a host.
And of course, that's incredibly important because whenever you're simulating an end-to-end system, the host side has to know what to expect on the device side, and the device side has to know what to report to the host side. So,
plus, this type of description allows you to generate that on the fly. Like you can, you don't have to upfront write your device or write your model. You can generate it, like from, for example, RTL description or RDL description.
And it's a single source of truth, which is important if you have continuous integration systems.
Yeah, that's that. So when we are talking about packetization and depacketization, Chris already mentioned that, but there are a few layers in PCIe that actually, a few different types of packets that can be sent across the system. So we do support two types of layers, two lowest layers in the PCIe stack. So this is a data link layer packets, DLLPs, and transaction layer packets, TLPs. That we can actually send back and forth between the simulated devices. So we have the whole logic for like provided the data, we do packetization, we send it over a standard Unix socket, receive on the other side, depacketize it, and just handle the data, like provide it to logic of the simulated device so that it can implement the rest there.
And I see a couple of people in the audience that I know have dealt with PCI Express. So of course, everyone here is aware that there is the physical layer as well. So one thing I could say is like, well, how do you handle the physical layer, the handshaking, that sort of thing? Like, how do you know if you're connected to a CXL system or a classic PCIe, whatever, Gen 4 or something like that? So do we have structure, Carol, in Warpipe to kind of integrate that sort of out-of-band information?
Yeah, there are additional functionality where you can actually add your custom communication, custom signaling for all of those. So it is super extensible. You can do that. It's thought of from the very beginning when we started implementing the library. And when we are talking about the packetization, it's kind of obvious that we'd like to see them. When you send the packets back and forth, you'd like to observe what's happening there. And the obvious choice for that is Wireshark. Wireshark is commonly used for observing bunch of packets everywhere, like Ethernet and so on and so on. So we did implement, like with the library, we do provide a custom dissector for Wireshark. So basically, you can just grab it, install, like by just copying it to a proper directory in Wireshark, in your local Wireshark installation, and connect to this socket that we use for communication between the simulated device, and simply observe the PCIe packets there. So basically, it will strip whatever custom headers we're adding to the standard packets that we send through the socket, and display more or less, as you can see in this slide. There is I think DLP, TLP packet showed here, and you can simply analyze whatever is being sent by the controller, PCIe controller in the simulated system. Super useful for debugging more complex system and checking what's happening there.
What I find fantastic about this is that it basically enables any end user, anyone with an FPGA, or not even if they just want to use a QEMU system and another host device or like a host system, you can actually develop most of your PCI accelerator firmware and inspect the actual PCI packets that you expect to see. Anybody can do this, and it's like open source, so there's zero cost. It's amazing.
Yep. So the library comes with a few, actually with many examples. I just listed a few of them here, but there is more in the repository. But those are like a kind of representative of what you can find there. So you can simply grab the repo, build those. There is a README. There is a pretty nice documentation of that. So one base one is PCIe pipe that connects two Zephyr instances. One is working as a PCIe host, and the second one is working as a PCIe device. And that one just exchanges the information between them. So basically, one node like host is reading a piece of memory from a simulated PCIe device, and then we have some simulated message signal interrupts sent back and forth. From the simulated PCIe device to a simulated host. The second one is PCIe native, which uses like a native application. So we don't have, if you want to focus mostly on the device side, you don't really have to simulate or like emulate or doing something special for the host side. You can simply use a user space Linux application for that and connect to the simulation of the device and focus on the firmware all running on the device. And of course, one of the core functionality of PCIe is DMA. So most of the devices work in a way that a device is actually issuing a DMA transaction to the host to and from host memory. And we do have support for that. There is an example of that where you can configure an emulated DMA device running on the emulated PCIe device that actually starts the whole transaction and starts the whole data transfer between host memory, either if it's a native host like a user space application or simulated host in yet another simulator. So that's actually like a typical flow of the PCIe device.
And of course, as we know in Zephyr, the beauty of device tree, because everyone loves device tree, is that you can swap out nodes. So whether or not we're using the emulated hardware in a QEMU target versus what we have in Zephyr is DMA emul, which is like software emulated. Actually, I have a pull request in draft at the moment. I should really get that up. But we have a DMA emul backend now that should be able to hook right into Warpipe. So we'll get that up soon.
Yeah.
That allows you to swap out the hardware sort of thing for a more software, which is a bit faster.
Exactly. We mentioned Zephyr a few times. I also mentioned that Warpipe itself, by design, is not really dependent on any type of OS or whatever you run it with, or runtime or whatever you use underneath. However, it comes with a few fancy features that make it way easier to integrate with a Zephyr-based system. So even if you if you develop Zephyr firmware for the device or Zephyr firmware or for the host. It's super useful to actually work with that. Do you want to grab that one?
Sure, yeah. Okay, so one of the key features that I asked for was actually Twister integration, because as everyone knows, Zephyr's upstream testing is done with Twister, and actually even at Tenstorrent, we're using Twister to do our continuous integration at the moment. It's pretty great. It allows you to test multiple permutations of things all at once. But it also supports multiple implementations of a thing, multiple architectures, multiple configurations. So you can swap out one emulated device for a physical device, and so on and so forth. So you can have actually the same test suite specifying your host software side of the test and your device side Z-test, and you can run the device in emulation, or you can run the device on physical hardware with memory map, or sorry, with a hard, what do they call it, the hardware map? I forget what it's called in Twister, one of those options. Mm-hmm. So in any case, what Micro was really great about doing was make sure that we could integrate this with Twister, and so that we could just hit the ground running with our continuous integration.
Yep. Yeah, and that of course required some work. It didn't work out of the box because it should have, but then you run it and then you find limitations. One of the limitations of Twister is right now that it assumes that it runs a single process underneath, because it is designed to basically build a number of configurations and iterate over the configuration, or select a random configurations that you would test, but in the end is always a single binary to be run. And here, since some of our configurations are like we need a simulated host and simulated devices, we need to run a few processes. So that one wasn't really supported, and of course, it's not a big issue to run a few processes. It's a bigger issue to actually control them in the end and to be able to actually observe if they talk to each other correctly and kill them in the end.
Or, what starts up first? There's a bit of a race there, but we have to be able to support that potential use case.
Yeah, of course, and not try to connect a client to a server if the server is not up, or still initializing and stuff like that. So we had to extend Twister to actually handle that. The code is open. It's in our fork. It's to be upstreamed in the following weeks, I suppose. But the code is there. So if you want to use this feature, you can always defer to the forked version or the version that is provided with the test suite of the PCIe Warpipe. But it's going to be upstream at some point. And one of the features that we also added here is a very simple device, PCIe device, and simulated PCIe device that we call memory mock, because in the end, it is a simple memory-like device. So basically, it is detectable over PCIe. You can connect over Warpipe with Warpipe to it, and simply dump a memory, write a memory, and do and observe the transactions between host and the device.
Of course, we're basically just talking about bars, memory bars, and the PCI terminology, and of course we support memory bars, and then as we mentioned already, MSIX and MSI. So.
Yep, exactly.
So this is potentially my favorite subject, because in reality, you're not always just testing QEMU to QEMU, or renode to QEMU, or whatever. Often on the host side, and I'm not going to stay left or right because it's going to be backwards, but often on the host side, you don't want to run a whole QEMU thing. You want to run like your gtest test suite, or you want to run something like that, like an application that's just talking directly to a socket, because we don't need to add additional complexity there. On the device side, you might not always be talking to QEMU. You might be hooked up to a gigantic hardware emulation system, because at some point you do want to test that this actually works. That could be your nightly runs, whatever. So the beauty of Warpipe being purely socket-based is that you can add an adapter on the device side, and that could be your translator to go from Warpipe socket protocol over to hardware emulation. And various vendors, I'm not going to name names, but various vendors have their own proprietary technology to do the exact same thing. So this adapter is basically just converting from the open source format to the proprietary format that you're not allowed to publish anywhere. So it actually enables a lot of people behind closed doors, which is, at Meta, this was quite important for us. I don't know if there's anything else I need to cover, but again, like both sides of Warpipe are swappable for virtually any endpoint that you want to put in there.
Yep. One of the quite important aspect of the development of the whole library was actually performance of the library, because if we go back to one of the first slides, I've been talking about we can always default to RTO simulation, which is slow. The whole idea of like getting moving that to ISS is to basically live with a complex simulation, but still be in the sweet spot of every computer scientist. I run the test and I have the answer immediately. So having performance was really very important. So there is a bunch of performance tests that are already derived with the library. And we do run them regularly to actually figure out all the bottlenecks, like especially in the places where you do packetization and depacketization, you can do it too much. Like you can split like a huge chunk of data into very, very small packets and then send them one by one, and that's super slow. Yeah. It's still probably faster than RTL, but it's not as fast as it can be. So there is a lot of work on that, like on getting that performant and actually analyze the bottlenecks and then fix them as it comes.
So as I recall, there was one performance bottleneck, which is ironically doing software calculation of CRCs, which is something that usually falls to hardware. Mm-hmm. So I think this is probably one feature where we could potentially disable it on the Warpipe layer, because that's not, like the upper layers are not going to care about that after depacketization. But it's pretty fast. Do we have a coverage slide, or are we?
Not sure if
So I just wanted to highlight this tool, just to refresh my memory. Is this Perfetto that you guys were using?
I don't remember top of my head right now.
Perfetto? I think it was Perfetto, which is the open source. It's multi-analysis thing. It was actually open source by Google, which is really cool. So I'll be using that on a few projects for sure.
The one there, I think, is SpeedScope, though.
Oh, sorry.
But there's just two options, Perfetto and SpeedScope. That
perfect.
And talking about coverage, if you go to the repository, you can run coverage tests by yourselves. There is even a coverage report there in the documentation, but the scripts for running that are there in the repository, so you can run it.
And of course, just a note on coverage, as anyone is familiar with who's working in this area, there are always corner cases where it's virtually impossible to get to with just hardware. So in some cases, you should be able to inject errors, that sort of thing, to get that, but coverage is actually pretty good. I think it was like 85 or
something like
greater than that, so it's quite good.
Yep. It's not all, there is still some work to be done, and some work is, some new features will pop up in the library itself. So first of all, one of the things that were impossible before right now are enabled is actually modeling of the routing or arbitration algorithms within like a PCI switches in the simulation of a bigger system. So right now this is doable. Of course, those models will have to be written, will have to be, the algorithms that are used there will have to be implemented or reused from whatever is already there. So this is something that right now is possible, but of course have to be done. The other thing is like a hardware control, like what if I reset my device? I need to have, first of all, this functionality of resetting the device and resetting the simulation on the other side and re-enumeration that in the simulation and stuff like that. But that's actually a pretty useful feature because it could happen in real life scenario. You may want to reset your device, especially, for example, in data centers. If you figure out that there is a hard fault on your device, and some of the PCIe faults requires you to reset the PCIe device. You cannot really recover from that. You have to start from scratch. But you don't have to reboot the whole system. You can reset only a part of that. And of course, in the end, a better way of designing like very complex systems. And for that, we actually work on, this is a project that covers way more than just designing complex PCIe networks, but it can be used for that. So visual system designer where we can simply connect blocks of, it's not just graph drawing. It's
introspection and
yes,
debugging and checking the consoles.
Generating the simulation code, generating the platform description from it directly. I know Michael sitting there will be presenting today later in this room a broader concept of visualizing everything, but this also happens there. So imagine you can simply connect those blocks, generate the simulation code, run the simulation code directly from it, or even do things like connect observers to certain lines and do these packet dumps and Wireshark observation from a certain lines on this graph. That's super cool. I mean, super useful and way easier for a developer that to understand what's happening. I mean, we know the code is better, and the whole tools are designed in a way that they do based on a coding first, but they can visualize the data and update the code on the fly.
Okay.
The next one is actually summary. So this is summing it up. Warpipe library, an open source one that you can just grab from the internet, permissively licensed. This is something that enables complex PCIe system testing in a way that will actually mimic the underlying hardware structure. So this is one step forward from what we have right now to stay in the like very, very fast simulation domain, but still be able to actually, simulate better what's happening underneath.
The one thing I forgot to mention, so I mean, right now we're talking about pre-silicon. I'm going to go back a few slides right here. So we've been talking so far about pre-silicon. What happens after post-silicon? You're still developing firmware, and you're still developing your host side stuff, either a Linux kernel driver, user mode driver, whatever it is. What's amazing about this topology is that you can actually containerize your host environment and use libvirt underneath. So if you have an adapter layer from Warpipe to libvirt, you're then actually talking to real silicon that you've gotten back from the fabricator. So
yep.
It's useful because, I mean, we want to do fast continuous integration. So from that perspective, it's useful even after post-silicon. Sorry.
That is true. So to get back to the last slide, please go to GitHub, grab it, run it, test it, report bugs. If you're interested in like some talking around it, some support for that, just you can hit us with this email, or just catch us here at the conference. We stood here.
And as well, if this is a space you're interested in working in, where you're doing hardware accelerators over PCI Express, I'm new to TensTorrent, but I feel like I've been there forever now because it's been amazing. So we're hiring. So we've got stickers. Come by, talk to me, and thank you.
Thanks.
All right, so we do have some time for questions.
Yeah,
I think like
minutes,
5-ish,
yeah.
6-ish minutes.
We can always,
Dan,
catch.
I can see you're thinking about something. Yeah. Do you have a question? Trying to wrap your brain around it. How can this make my life easier? It sounds like it can make my life easier. It can. Anyone in the hardware space? Alexei?
Okay, so since I have a microphone, yeah, so in Synopsys we obviously do something similar, but we are mostly interested in more interface-ish part of the thing, but not about data transfer, because, well, that's what some other team is doing. But in that sense, So okay, so it works with Kimu, it works with VNode. So what about something else? So for example, for me, it would be interesting to integrate that with some more proprietary things like virtualizer, which we have, for example, or with VCS, which is RTL simulation.
Absolutely.
So if I may sell it, that kind of tool, which is very amazing. So why not?
Well, that's the beauty about Warpipe, is it's a very permissive license. So we haven't made any kind of standard for the packet format, but they are standard PCI structures. So, and of course, you're free to use the library in any project you want. If you want to provide an adapter to this open source interface to your customers, that's fully supported. So.
Okay, cool. Thank you.
Okay, I suppose we can catch up somewhere in the hall, unless
Yeah, Holy Track. We'll get a coffee or whatnot. Thanks again for attending.
That's a run. Yeah, time for a break.
1, 2, 3. Okay. Seems to be working. Let's see if I can shift slides. Okay, I can. All right, so let's wait 1 more minute. I can see some people coming in. Hello. All right. So I think we'll get started. Hello, everyone. I'm Michael. I'm from Micro, and I'm going to be talking about a new methodology tool system that we're building. It's had various names, but we kind of call it Visual System Designer. And we're going to be showing you some interesting stuff about generating code, generating like system descriptions out of diagrams, and with some interesting connections to Zephyr and other things. So I wanted to start with the observation that if you're building real systems out there in the field, supporting real product families and kind of complicated configurations of products and multi-node systems, this really changes your perspective on development. It's very much different from building something on dev kit. And so if you really want to build things like space satellites or cars, you run into a whole set of new problems that you wouldn't really encounter if you were just doing work with a dev kit. So that change of perspective kind of gets you to think about things a little bit differently. And of course, some of the problems you might encounter, and in fact, we can see that not from a user perspective, but from a vendor perspective. If you have, a silicon vendor that has, 100 dev kits or 500 dev kits for their own silicon, they'll see that in order to work efficiently with this kind of complexity, there's a lot of configurations you have to take into account. There's variability. There's different variants of boards. Throughout the life cycle of your product, your BOM might actually change. So you call something board XYZ, but over time, board XYZ actually becomes a different board because you have to use different components because some of those have gone out of use and so on. And of course, at that scale, you're probably not working alone. You're working in a big team. There's many folks. There's many people geographically disjoined. There's perhaps several companies collaborating. So how do you really tackle this? This is, of course, a very big and important problem. And there's no one solution, but I think there's, of course, a very kind of obvious solution that I'll kind of talk about in a second. And complicating things further is the fact that we have a hardware landscape that's already pretty complicated, but in fact, you want it to get more complicated. You want to see more silicon, more chips, more modules, more boards being published. And in fact, we're very happy that this is happening. I think we're seeing a renaissance of new silicon being pushed out by everyone. ST, Analog Devices, NXP, Texas Instruments, and everyone's building new types of silicon, higher and higher end, more diversity. The product portfolios are getting more complex with people offering ARM Cortex-M, ARM Cortex-A, RISC-V, it's a growing market too. So overall, this landscape is really complex, and it's even growing, right? So the problem's kind of getting worse in a sense. This is exciting, of course. Like we want more hardware. As people who work with hardware, we want more of it. But at the same time, of course, picking the right thing and making it work in an ecosystem of your products might be pretty challenging this way. So in fact, the answer is obvious. We're here at EOSS, and you can tackle this with open source. You can kind of make sure that by collaboration, even though the complexity is growing, you're kind of staying in front of a charge. You're staying kind of capable of managing that complexity. But to do that, you need some tools. Of course, one of the things that I'll be talking about today is Zephyr, because Zephyr is a very good answer to this complexity. Zephyr has had this baked in from the very beginning. It is based on configuration. It is based on a methodology that allows you to work with systems in a structured way. It doesn't just throw a bunch of code at you. There's configurations, there's device trees, there's a lot of depth in Zephyr that will allow you to build your products in a much more structured way. And in fact, with the hardware model 2 that has just been introduced, this gets even better, because hardware model 2 tries to address this problem of complex hardware, like hardware with 2 SoCs on it. How do you represent that? And I think it's a step in the right direction. It's of course not everything, and still there's a lot of work in terms of figuring out how to make Zephyr work for advanced hardware with multiple cores and so on. And not everything's fully perfectly standardized yet, but it is really going in the right direction, and Zephyr has been pretty incredible in finding a community-based solution to the problem. It's not a single vendor's idea that's driving this forward. It is a collaboration of a variety of different people. It's, of course, the silicon vendors themselves to a large extent, but it's also different kinds of companies that build products or deliver services. Everyone just tries to figure out a way that serves their own purpose, but by combining those purposes, you can find pretty good solutions. And the hardware model version 2 has actually been a pretty good idea. So here you can, of course, see some advanced NXP device with some multi-core capabilities, some Cortex-A, Cortex-M. You could run Zephyr on either of these, of course, or you could run Linux plus Zephyr. So kind of representing this properly and making it easy for people to actually do that is a challenge. By the way, the migration itself is a nice example of a collaboration. There's been a lot of course, hard work and discussions and delays and so on. But generally speaking, for example, you could see that people actually collaborating across the board, right? So you didn't just have everyone taking care of their own things, to some extent, yes, but you also had people helping each other out. You had Nordic actually kind of spending a lot of time and work to get other people's silicon across the board just to make hardware model 2 happen, right? So that's a pretty incredible way to collaborate around describing hardware, where yes, everyone has the responsibility for their own stuff, but if someone really wants to make something happen, they can also help other people to make it happen. And in fact, it does happen in practice, that you get this kind of collaboration, even between companies that nominally compete, right? So I think Zephyr enables this kind of awesome collaboration, even between competitors. And we are also developing a tool called Renode, which gives you the ability to simulate systems. Now, to simulate systems efficiently, of course, you have to model them. That's something you can't avoid. So you have the device. You normally write a driver to make your SPI peripheral run. On the other side, you'll have to build a model, and that model will have to describe what this SPI peripheral is doing. So there's non-negligible work involved in doing that. Having said this, there's a lot of great stuff that comes to your rescue. And it's the same as in Zephyr. You have a driver that might be addressing a certain peripheral. If that certain peripheral is present in a number of different boards that are related, what Zephyr does is it takes configuration, it addresses this via device trees, and you just instantiate the same driver, perhaps on a different address, perhaps with some configuration options. But generally speaking, you reuse code all across the board in a very strict and efficient and configurable manner, so that you don't duplicate code all the time. So if you're building a BSP for a different board that happens to be similar to another board, has the same SoC or a similar SoC from a similar family, you'll probably just mostly tweak configuration files. Renode does the same. So if you have models for certain peripherals in a SOC, if another SOC uses the same kind of stuff internally, then getting it to work in Renode is going to be very easy. So yeah, our simulator is kind of course, an open source tool itself, but it also benefits from other tools that are open source. And one of the things that we built is called Zephyr Dashboard, which essentially takes all of Zephyr, takes all of the 600-something Zephyr platforms, and runs, compiles binaries for those platforms in the standard way. Zephyr makes it very easy to kind of just compile a binary across 600 different boards. And then what you do is you run it against Renode, where you just generate the configuration for Renode dynamically from device trees. We have a tool called device tree to REPL that just takes a device tree, generates the Renode description. And you just kind of run one against the other, and you hope for the best. In fact, you don't have to hope for the best. There's 470 targets that we support. So in fact, we cover like 75% of all of Zephyr. And naturally, that does not mean we cover the entire silicon space, with all the peripherals and everything. We can run basic demos on 470 boards, and there is a lot of complexity involved in actually supporting all of them perfectly. But there's a great starting point for very, very many boards in simulations. You can just, in fact, this is a public website, it's a public CI where you can just go grab the binaries, you can take a look at the outcomes, and there's a lot of data that we can generate this way because Zephyr makes this data available in a sense. We transform it, we build it, we run it, we generate traces, we generate a lot of information on top of this, and all of it is open source and then free for everyone to use. And it's a great example of how those tools can reinforce each other, where configurability, if it's baked into both of them, it gets very easy to integrate them. So this is one way that we can kind of handle this complexity. So of course, here we're testing across a range of different devices, different dev kits. But what you might do in your product would rather be you take a lot of different configurations of the same product, you take a lot of different use cases, and you run that in a massive CI. You run a lot of corner cases, you try to figure out what's breaking, what's working. Commit after commit after commit. So this runs after every commit of Zephyr, right? And we have data for Zephyr, like how is the performance of Renode versus Zephyr kind of improving or getting worse. There's a lot of demos and different kinds of scenarios that we have here, including AI and Rust apps, and so on and so on. So it gives you a lot of insight into Zephyr. Now, interestingly, of course, I'm saying about this interoperability of different tools. And in fact, we've seen this in practice already, where because we're running this dashboard, because we're building those tools, we are finding inconsistencies. We're seeing that, well, yeah, this is great, but it could be better if we did it a little bit differently, if we encoded our device trees a little bit differently, or we updated those strings here, our data would be cleaner, nicer, more relevant. And so we go and contribute those changes back to Zephyr. So you will see us making those random pull requests every now and then, just fixing random things in device trees. And if you wonder why we're doing this, well, we're doing this because of that. And this is fun because, of course, you discover inconsistencies, and you guys are engineers, you know how it works. If you find an inconsistency, someone's wrong on the internet, it's always fun to fix something, even if it's a tiny thing. So, you can see how, working with one open source tool actually gets you on a pathway to fixing other open source tools because it's to your benefit. It's not even that you're a nice person, it's just that it happens to benefit you to fix other people's stuff. And much like in the previous example that I mentioned with the hardware model itself, people just help each other because it's good for them to do so. Now, so summing up this part, in the real world, this kind of structure that I talked about, this kind of single source of truth approach that I'll call it, is not just a useful thing, it's essential. At a certain scale, like we couldn't ever build the Zephyr dashboard, by hand or by some clever hand-generated stuff. We would have to really spend a lot of time to do that, and we couldn't maintain that. Instead, we rely a lot on automation and the data being correct. So we just have to find ways to work differently. We have to find ways which don't involve engineers spending time on tweaking little things here and there. It has to be scalable. So we use the device tree as a kind of common data model, and that feeds both Zephyr and Renode, and we make sure that those are correct because both our Zephyr work and our Renode work needs this. So we've gone on a quest to find consistency and structure in the hardware landscape. And that quest has, I think, been going on for 3 years now. So it's a kind of a massive endeavor on our end where we actually did a number of things in sequence. I told you about the Zephyr dashboard. But based on top of this, when we saw, okay, we have so much data, we have so many boards that we can run, we thought that, okay, we could perhaps take this data and present it in a different way. So we built a tool called Renodepedia, which is an encyclopedia of hardware. And that Renodepedia is, showing you those demos that we run in the CI in a more visual way, with traces, with everything. It was a fun experience and very useful. We still use it ourselves as a reference, and our clients do too. So Renodepedia was a great step forward. But then we felt that, okay, there's more we can do, and we also built something called the Open Hardware Portal. We do a lot of hardware, and open hardware is something that we engage in very, very much. Of course, we build proprietary hardware for our customers, but when we have reference designs, when we have kind of ideas for new boards and so on, we will, of course, try to make them open source when we can. So we have like dozens of open source designs, and we thought we needed a home for them, so we built this hardware portal. We call it Open Hardware Portal, which both hosts an open source component library that we're building. So all of these boards are built in KiCad, and we're using Blender to visualize them, and then our component library is also open source with Blender models and everything. And we just host it through a portal. And again, we're kind of looking at the landscape of devices and chips. We're like trying to see patterns, trying to categorize them, trying to make sure that we can display them in a one nice and cohesive way. And then the third thing we did was on the top. It's a tool we call Visual System Designer. So it's been around for a little while, but it actually right now is kind of growing up to be a real tool. So last year we kind of made it, and we kind of made it in a way that you can describe a system visually. Now we're actually kind of combining it with the other efforts. And we're building a system that allows you to visually represent your embedded devices and to do some fun stuff with them. And by fun stuff, I mean serious work, not just kind of demos. So like all of these things have been a very good learning experience, because all of them required us to work with data and clean up the data and figure out ways to parse, the massive amounts of data. Like, to put this into perspective, Zephyr has those 600 boards. We have thousands of components in our hardware database. In every SOC, there's many peripherals. If you count them all together, again, it becomes like hundreds or thousands perhaps, because there's like hundreds of SOCs, thousands of IPs in those SOCs. So overall, it's a massive scale. And figuring that out has been a really challenging thing, but also very rewarding. And we haven't only focused on Zephyr. So over time, we realized that, yeah, Zephyr is a great starting point. It's a very tidy and nice operating system with a lot of data in it. But of course, if you want to go and target the entire ecosystem, you need to also use U-Boot and Linux, and perhaps some data from vendors, and perhaps Platform IO. There's different places on the internet where you can find structured information about hardware. The challenge is in pooling this data together and actually making it sensible. But we're trying to kind of make that work. So what we're essentially building right now is a system to describe and manage entire multi-device systems you're building. So I'm giving an example here of an open source hardware setup that we're building. This is a GPU cluster that consists of mechanics and a bunch of boards and a PSU to power it and so on. And all of these can be represented in this tool. And for kind of every piece, you can drill down, go into the actual components, see what's there, and see what software is running there, and so on. So this is a pretty massive, of course, piece of hardware. But you could do this on different scales. Like, of course, it doesn't have to be a GPU cluster. It could be a smartwatch. It could be any kind of device that you're running, a medical device, a satellite that I showed before. The importance is in the connections. Like, you create a connected database of whatever goes into your device. And in fact, all of this is based on open source data. Like, we have this database of components. We have the Zephyr data. And we are looking for a way, we're building a way to expose that data in a nicer way. You remember Renodepedia? This is kind of similar, but much broader in its kind of ambition. We're trying to present this data in a way where you can search things and kind of explore what kind of SoCs are there on the market, what kind of cores they are inside, what kind of I/O they have, and so on. And the interrelations between those elements are very important for us. As a slight detour, if you look at different kinds of devices on the market, for example, you will find that there's an Ethernet controller, for example, that you find on a RISC-V board, the PolarFire SoC. The same Ethernet will be found on, for example, a Atmel Cortex M7. And the same peripheral is going to be found on an UltraScale Plus, which is a Cortex-A device from AMD Xilinx. So a very broad range of hardware can actually share common components. And it's not very visible normally until you start working with this data and until you realize that there's so much IP reuse going on between the silicon vendors. There's so much structure in this. So it's kind of interesting to work with. And one of the things we want to enable is, like, when you're kind of making choices, like, what SoC am I going to try to use and so on, you can filter by cores, I/O, and just make your design decisions this way. And of course, like before in Renalpedia, you can have those demos that we have a CI that builds demos for all these boards that we have Zephyr running on, and then those demos, you can just look at them, you can look at the results, you can reproduce them fully. This is all like open data, so you can get into any of these data demo, and there's just both Zephyr and U-Boot now, so you can grab the relevant binaries, you can look at the UART logs, you could look at the trace outputs, and it's a great starting point, right? Because if you took a dev board, you could basically grab a binary from here and just run it, and it should work. We actually do it ourselves. We kind of use this resource ourselves internally when we want to get started quickly. But existing boards are kind of boring, right? Like you actually want to build things that are new. So I'll get there. So we, for example, develop hardware for our customers, for ourselves. And for this hardware, we typically have some more data. Like we have data about their design. And we can, for all those open boards, we can actually generate 3D renders. We can actually generate like hot areas where you click on a component, you go to that component. And then you can also generate data about the stack up of the board. You can preview the schematics online. There's a lot of depth there that you can explore. And of course, we don't need all this data. Like if you're missing some of this data, then you just don't get some of the features. But if you have this data, and very often, we don't actually need the actual design data for most of these things. It's enough for like production Gerbers and placement files. So this is pretty cool. And one of the other things that you can do if you have this ability to describe a system in a coherent way, you can generate software bombs, you can generate hardware bombs. And of course, our software bombs is something that Zephyr does, so we're kind of leveraging the capability of Zephyr. Hardware bombs is actually something that's being standardized now in a HBOM work group that's led by Kate Stewart. So kudos to her and leading that group, where as soon as a standard emerges for doing this, because we don't have a consistent standard out there for telling people what your hardware looks like, as soon as one emerges and we're helping define it, we can actually use this information to generate whatever you need, right? Because we know what the system is built from, we have all the components and so on. So now getting to the visual system designer itself, if you want to represent that kind of structure, of course you can just write it in a file, right? But we felt that there has to be a better way, or at least another way that you can augment your work. And we came up with this diagramming-based solution where you have a diagram that basically describes the connections. It's not a schematic, right? It is a block diagram, so it operates on the level of I/O, like SPI, like I2C, like PCI Express, or connectors that you connect physically. So this actually presents this GPU cluster. So there's 8 different GPU units and the main board. It's a pretty nice structure because, of course, it's very logical. You just want to run 8 GPUs together and coordinate between them. So you can describe your device this way, and that gives you a lot of interesting capabilities. So of course, it gets interesting, especially as you take different elements that are active, right? If you take SoCs, if you take sensors, if you take actuators, you can turn them into boards where you run software. And then, of course, it's kind of funny when you're building a new board, the delta T between conceptualizing the board and getting something working can be very long. You both have to develop the hardware, and then once you have the hardware, you still have to develop the software. And it might be a while before you see any result. And we want to change that, right? And we want to change that not just for dev boards, we want to change that for any kind of custom boards. So in fact, what we do is based on the structured device tree data that Zephyr has, we parse that, we kind of analyze that, and we can generate board files, device trees, and test binaries. And when you do that, you realize that, oh, I could actually have a test binary for anything. Of course, having some assumptions in place and so on, but generally speaking, Zephyr is very flexible in explaining how things should be connected. So with some clever heuristics, you can get very good coverage of different kinds of systems. And we can generate binaries for quite a lot of different SoCs connected to different sensors. and it just works. And when I say it just works, it's because you can then take those binaries and you can actually run them in simulation. Because as you remember, if we have the device tree, we can also generate a simulation file. So you put those two together, you get a full feedback loop. And with that, I will actually transition to a demo. I hope that works with this screen setup that I have now. But I did want to kind of show you how this would work in practice. I just need to fire up something in my terminal, or I'll start with the system itself. So, yeah, let's see how that works. It's going to be fun clicking things on this other screen, but I'll take my chances. Or will I? Yeah, that was the wrong button. So, yeah, it's very dark here. All right, I think I got it. That's the full screen button. Okay, so this is the system itself. It's unfortunately very bright in here, so I hope you can see something. Basically, we have all those levels I talked about, right? This is a web page that pulls it all together. Of course, you have the device level, and then you have the GPU cluster. Right here. You see the GPU cluster. It has all those things in it. And you click one of the boards, you kind of get into that particular board. Because we have the 3D assets here, we can actually flip it. So it flips. It's an actual animation we generate out of Blender. This one is not very interesting because it has no active components on it. But if we go to boards, for all of these boards, of course, we have some Zephyr demos, but there's one that I have a special demo for, and this is this entire flow. So this is an environmental sensor we built with an ST chip on it, and some sensors, of course. And for this one, we have a block diagram that we created. And our aim is to actually generate those diagrams automatically as well for all of the Zephyr boards. But for this one, we kind of drew it by hand. And this diagram is special in that it isn't just a drawing, right? It isn't something that you just look at and think, oh, my system is very nice. Let me look at it. You can click Edit this diagram here. Again, sorry for the lack of visibility. And you will open an editable version of this, right? So you can take those components there on the left-hand side. You have like displays, I/O, sensors, you name it. And you can connect them up together. And those connections are actually meaningful. So, you know, this is not just randomly connecting things in Draw.io or in Google Draw. This is connecting things with the understanding that a GPIO can only be connected to a GPIO and so on. So there's a specification driving this that dictates what components are available and what things can be connected to each other. And so we have this diagram, and it's looking pretty nice, but let's do something fun with it. So let me just run the backend here. The backend will be running on my computer, but you could, of course, run it in the cloud. And now we can actually press the play button. And you can see that I pressed play, and we have a backend that just builds the Zephyr application. And I didn't have any board files or anything else on my computer for this before. So I only have the diagram, and I don't have knowledge of how Zephyr works. And from that diagram, I generate the device tree and board file. Of course, then the binary compiles, and once it gets compiled, it should start simulating. Let me see. I can't see very well on the screen. OK, so starting simulation. And I'll have to close the terminal just to show you. But here we have an LED that's blinking. And this is the real binary running in simulation in Renode. And this binary actually connects back up to Renode, back up to the front end. And we have the LED really blinking. And there's some temperature sensors getting temperature readings. You can see the UART output here. So there's a Zephyr console. We see the LED state. We see 20 degrees being represented here. And we could actually, I'll try to be a little bit kind of creative here. So yeah, the problem with my setup here is that I don't see it very far into this. I'll actually move this a little bit closer to me. I can do that. It's interactive. And there you have a temperature, right? So we can just edit this, and perhaps I don't know how much. OK, let's make it 1. So hopefully I made 1 degree. No, I made it 19, I think. Okay. So anyway, yeah, I just took it down a notch. So now we have 19 degrees. We started with 20, now we have 19, and so on and so on. You can actually go and modify the diagram. So of course, you'll have to stop the simulation for that. So I will kind of go and stop the simulation by kind of clicking here. And now I can grab an LED. Let's take this one. And this LED, it has a GPIO connection. I can move it to the other side here. And I grab the GPIO connection. Sorry, this is overlapping here. So let's grab the GPIO connection. I can only connect the GPIOs. The only green ones are here, are the GPIOs here. Oh, okay. And now I hope it works. So now I have another LED, right? Let's regenerate that. It'll take a while, of course. Let me just try. Okay, yeah, here we go. So if we minimize this, you'll see that both of the come on. Okay, you know what? It's very hard to click here. Yeah, okay. So both of those LEDs are blinking now. And this is being regenerated live, right? So you can, of course, like take away sensors, add sensors, change stuff as you wish. So that's the demo. Of course, like there's much more depth here. You can explore the database and so on. But I think hopefully it kind of visualizes to you how it's all connected and how it's relevant. And in fact, one of the things you have to understand is that we can also do this for multi-node systems. We can do this for complex systems that run multiple binaries on them. Out of necessity, the demo isn't much more complicated than this, but you could just scale it up to more boards. You could connect boards over CAN, or, and all of that is supported in Renode. And the major challenge that we're facing is, how do we represent this graphically, right? We can make it happen on the command line, and we're trying to give people a tool that will also allow them to do this graphically. So I'll close this now, and I'll try to return to my slides, which I managed to do, I think. And so you can actually hear more about the specifics, the details of how it works in another session that comes right after mine, which is going to be showing this, but not in the context of an STM board, but in the context of a pretty complex multi-core FPGA-enabled device. My colleague will be kind of getting into the details of how that works and why are we doing it for FPGA-based RISC-V devices and so on. So you can see that if you're interested. About future plans, and that'll be kind of very quickly to wrap up. First of all, we need to release this publicly. So the system that we're building is kind of very new, so it hasn't been released. It will be released in the next few weeks, and in fact, the entire flow is open source, right? So if you want to reproduce that, there's a link here. It's not very visible, but you'll get the presentation later, and you can reproduce this. And the portal itself, the tool that we're showing here, is going to be released and public. So it's just a matter of a few weeks, I guess. We also want to have like user profiles where we can kind of save data and have private projects and templates and stuff like that to enable people to not only just work with generic boards or perhaps play around and finish and go home, but more like persist their data and try to build real systems. And of course, we'll be using it internally too, ourselves, to build our customer projects. And generally speaking, we want to enable you to like express your system and then get our help to build it, right? Either on the hardware side or software side, perhaps build simulation, perhaps build Zephyr or like an over-the-air update system. Like the sky's the limit. We want to make sure that you can represent your system properly so that once we know what it's comprised of, it gets easier to discuss what can be done with it. And with that, I'll leave some minutes for questions. Thank you very much.
So thanks for doing that. This is super interesting, especially from a sort of a lens of CI and continuous builds, and that alone makes it worth it. But so because it's cross-platform in software, cross-platform in hardware, what's the complexity behind the scenes? How brittle is this right now, or can I pick it up and run with it today?
That's a very good question. And, you know, we don't really know how brittle it is because we haven't tested it so thoroughly as we'd like. I think that if you just took it and ran with it today, you'd definitely run into rough edges. This is mostly because when we parse the device tree data and so on, there's still a lot of inconsistency and things to figure out. There's no unsolvable problems there, though. Like, we don't believe this fundamentally should be brittle long term. It's a matter of it being new and you know, kind of us building it up as we go and being excited about it. Of course, we try to present it at an early stage, right? So definitely I wouldn't recommend it to you. I mean, grab the repo, try it out for yourself, but don't use it for a production system yet, right? We will be actually the party that starts using it for the production systems, just so that we can kind of continue sharing this methodology with others as soon as we know it's safe to use it without, you know, our supervision. So I guess definitely there's some brittleness, I'm sure, but most of it is just, you know, we're parsing data with Python most of the time and generating things. And the better the source data becomes, the less brittle our algorithms become. And typically it's a lot of just string parsing, really, and you know, device tree compatible strings, you know. They used to be kind of here and there, but they're much more precise today. The hardware model version 2 is helping, so it's all converging in the right direction. But as for, like, is it production ready? Probably not. But we'll be the first to tell you when it's, you know, okay, it's production ready, you should do it. Right now, our focus is release this portal so that people can actually, because you can experience it from a command line today, but that's not as much, like, that's not as awesome as we'd like, right? What we want here is, you know, you fire up the portal, you wire up renodes to the portal by just running a command line, you know, command. It's pretty simple. And then you can play around with different things. And only then you actually expose all the interesting things you could do, which are kind of the same that you could do with a command line, but it's just that the portal aspect, the exploration aspect, gives it a whole new dimension. And I think, of course, uncovers a whole new can of worms and set of problems, but that's good. We want to solve those problems.
One follow-up. You also mentioned that because of the common IP blocks used across many different parts, you can sort of get a bigger bang for buck. I work in custom silicon. How would I go about plugging my IP block into this system?
That is an excellent question. So in fact, one of the other goals that I didn't dare to mention is silicon development. So we work with open source tooling for silicon development, open source IP, and generally we do help silicon companies build chips. And we do want this to be integrated into the portal. We just chose, we pick our battles, right? So boards and systems are kind of a different use case, similar because it's all, again, interconnected and so on. So we have the encyclopedic aspect of, you know, IPs and SOCs and so on. We don't yet have, like, the design capability where you go into a SOC. And I mean, we have it internally, right? We have a proof of concept. We have a lot of work in that field. But how do we plug it back into this publicly available system is just a lot of work. But we definitely want to do it. We're involved in things like Calypso Root of Trust. We're involved in OpenTitan, OpenSecura. You know, we're involved in a bunch of open silicon projects, which come with a lot of open source IP. And of course, there's also proprietary IP that's very interesting that, you know, you can kind of put those both together and perhaps build a chip out of this. So we definitely want to enable that use case. It's just not going to be the first on the roadmap. But, you know, it kind of depends who's asking as well, because, like, if we have people that say, oh, this is awesome, we totally have to enable this use case today, we're flexible to doing that. It's just a matter of picking your battles and, like, gauging the interest. Like, where do we see the most people getting excited? And then probably this work will go whatever direction we see is being useful. Of course, some of it is just driven by our own projects. So, you know, if we have a lot of, like, product development projects, then perhaps the product development side of things will develop faster. Versus if we have a lot of silicon projects going on, suddenly you'll see features popping up related to silicon design, because we kind of tend to build tools that we use ourselves. Renode originated, for example, as an internal tool that we only open sourced after a few years when we realized it's useful in a broader context. So you will see a lot of our stuff when it's popping, like when you see some open source releases from Micro, it's typically a customer that's driving them, or at least a use case that targets a group of customers.
Thank you.
Some more questions? No? One question from my part. So you're generating device tree. So I guess that it means that you're generating all the pin control, clocks, and so on, clock configuration, and so on. Yes.
Yeah, yep. Of course, and I think there's quite a lot of work to be done in that space, especially. So we'd of course generate some default values, and how do you actually make it easy to graphically configure like stuff like pin control is one challenge that we have to tackle. So good point. And right now we would just generate, whatever is the default. But I assume there's, some things that people might want to tweak in that regard. And we've already talked about that. We already have plans how to do it. It's just a matter of implementing this.
Okay. Thanks. No question? Okay. So thank you. Thank you, Michael.
It's green, it's ready to go. So.
Test. Testing.
I might have you muted.
Okay.
Oh, okay, 1, 2, 3.
And I'm still muted. Test, test. Turn on your mic, though.
Okay, so shall we start? What time? Sorry?
Okay, so we have some time.
Do not adjust your television.
So, hello everyone. Thanks for attending our presentation. The topic today is about one audit, a security audit that happens on Zephyr, and some experience with vulnerabilities that we have. So, who we are? I'm Flavio Solim. I work for Intel. I'm the current security architect for the project, I believe for the last 2 years. And before that, I used to be the security chair.
And I'm David Brown from Lenaro. I am the security chair for 2 years, and before that I was the security architect.
And all this time we are part of the PSOR team on Zephyr, and we have worked with things related with vulnerabilities and security in general in the project. So that is the agenda for today. First, introduction about Zephyr in general, the history about security on Zephyr. Then we'll take some time looking past vulnerabilities, try to get some insights from this information. Then we move to the audit itself that was done, some lessons that we learned with this audit, and what is the outcome from this, right? Which strategies were implemented, and we are thinking to do on Zephyr to enhance security in general. And finally, some conclusions about the whole thing. So let's start with embedded system security, right? So if you go to the Zephyr's documentation and try to get a description of what Zephyr is, you get this, that Zephyr OS is based on a small footprint kernel designed to be used in resource constraints and embedded system. And by embedded systems, we mean a specialized compute system that perform dedicated functions. In general, with real-time constraints, and are embedded as part of a larger device or system. This means that the security for embedded systems is very critical, right? Because we are not only talking about isolated devices, but devices that are connected to a much bigger and a complex platform. So we need to worry about this. We need to worry about data protection. We need to protect private data from unauthorized access, that it's crucial. We need to worry about integrity. Sometimes these devices, control critical process in an industry or healthcare, or it's part of a bigger automotive. So integrity is pretty important. We need to not allow that when this device is compromised, this will compromise the whole platform that it's inserted. So another thing, when talking about embedded in this world, we need to worry about availability, right? The system need to be responsive. So sometimes if it loses, if it's disconnected or it's not available anymore, that can cause cost issues and other things. So it's pretty important, worry about security in embedded systems. So, and what Zephyr does about this? What is Zephyr history for security? What can we do to prevent these problems? Provide security features is not enough. Software contains problems, obviously, and people do mistakes. And there will always exist people ready to exploit these mistakes. So what we have to do is basically minimize these mistakes and properly deal with the ones that will appear, because they will appear. So what we do on Zephyr, what we try is provide a framework for developing security systems. So we offer a lot of features that can be used. We have memory protection using MMU, MPU. There are security boot, trusted firmware. There are other features that are provided as external modules. So we have a whole history for crypto. So these features are there. We have other things like stack canaries, stack guards. So there are mechanisms to help to develop a software that contains some ways to prevent some of these issues. But that, as was mentioned, that's not enough. We have to deal with the problems that will appear. So Zephyr has 2 working groups. We have dedicated for security. We have one committee that it's the oldest one, and it used to be the only one where we talked about security, we discussed security, we handled the vulnerabilities and the issues that appeared. That is closed to the company's members, but at some point we thought, there is no reason for most of the things that we are discussing here be closed. So we are talking about improvements, enhancements, and things that apply for everyone. So we decided to split this. So we created this security working group that it's open to the whole community, where we discussed basically features and how to enhance in general, security on Zephyr. And then we kept the security committee that it's basically dedicated for talking about vulnerabilities that are under embargo and other minor things that related with budget and how we'll, do things that require, money that comes from the companies. So we also, provide regular, updates. We support the last release and the release pre-order with security updates, plus the current supported LTS versions. And when we talk about vulnerabilities, the way that we identify vulnerabilities is using CVEs. CVEs are a great way to do this. It's provides a unique identifier, not only inside your project but in the whole ecosystem. There is a whole ecosystem using CVEs. So there are databases that you can query to check if a product, or if a specific software is affected by a problem. There are tools that can check this automatically to you. You can integrate this with your SBOM, so CVEs are great. But how we assign these CVEs, right? Once we have a vulnerability and you decided that should be a CVE, how you get a number assigned to this? So for that, you have to be a CNA. And it happens that Zephyr is a CNA since 2017. So we are able to assign our own CVEs and publish them, and that it's good because we don't need to to work with a different agents or to get this. We don't need to synchronize our vulnerability process and dates with them, and the same thing to publish. So we control the whole chain for that. As I mentioned before, we have on Zephyr a absurd team that it's responsible to, once we decided that something is a vulnerability, to deal with this. So how we, having a vulnerability, created, a CVE assigned, that it's not enough if you don't use this properly, right? So we used in the past having this information available for the members only in the project. But then we decided to expand this a little bit, so we created this alert, this mailing list that people can have early access to these vulnerabilities to know, something was figured out. So what is the plan? What it's affecting? How I get ahead of the problem in my products? The policy for Zephyr to handle vulnerabilities is the embargo period is 90 days. The goal is that we have the problem fixed in 30 days, and then we have 60 days to downstream this, the fix and let some room for people update their products and or the software with the fixes. That it's open. This mainly is anyone that it's a product maker. It's using Zephyr, wants to be ahead of the problems before they become public. They can assign to the mailing list. So now we can jump to the vulnerabilities on Zephyr and have some idea of what we found in the past. So to start, let me just give some context. We used to track vulnerabilities using Jira in the project in the old days. That was okay, it worked for some time, but we still have some problems. First, it was hard for people to report issues there. They need to create an account. They need to sign Jira. They need to publish the, to report the problem. And that was, caused some traction, and people were not really reporting, or we thought was a problem. The other thing is, once we created the issue there, when we were tracking there, it was hard to assign someone to look there, because even our developers, they had to have an account in Jira to be able to see the problem. But that is what we had at the time. And then, the GitHub created this advisory thing, and we thought, well, why not we move it to GitHub, right? Since everything on Zephyr now it's using GitHub, so we moved it to GitHub, and it was good. They provided a way to handle this. It was much easier to assign people, to give visibility for people, because everyone basically working on Zephyr already has a GitHub account, and people that were used to report issues to us also have GitHub accounts. So that makes this. So the vulnerability, the whole thing, the whole point to talk this context is that all the vulnerabilities that I'm going to show here are from the last 3 years. That is since we started using GitHub. Yeah. So all the issues are on GitHub. CV. I don't think I have talked what exactly it states. So CV states for common vulnerabilities and exposures. So, when I started looking for CV, for our past vulnerabilities, some of the things that I really wanted to know was how frequent we are, receiving vulnerabilities. Is this somehow related? We receive more vulnerabilities as soon as we do a release, or it's priority release, or when we do LTS releases where we get more reports. And so I query the data. I try to get this. The other information that I really wanted to check is, what is the most common vulnerability that we are facing? And what are the areas that these vulnerabilities are being found? So we got this data. So the first graph that you can see here is the frequency of the vulnerabilities. This shows when the vulnerability was created on GitHub. You can see that we have some outliers there, especially in the beginning of this graph. And the reason is because in the beginning we were basically migrating all the data that we had in Jira to GitHub, so that it's why we have this big outlier. The other ones, I couldn't find any, particular connection was not really, close to a release. It was not after a release. The only one that I really know what was the cause that we got, some sort of spike in the number of releases was close to the end of this graph, that it's caused because there was an open source training, for security, and the guy mentioned Zephyr and shows some use cases on Zephyr, and then some of his students start looking at Zephyr's code base, and they found, some vulnerabilities in our code. So yeah, so that was the frequency. And then was, what are the areas, and what is, how critical are these vulnerabilities? The majority is critical, so you can see, or they are, or high or medium. We barely have, low vulnerabilities based on the CVSS score. In the areas, it's not surprise as well, right? Most of these vulnerabilities are found in network and Bluetooth that are, big areas, complex. They tend to be more complex than the other subsystems on Zephyr. And finally, what are the most common type of vulnerabilities? Here you can see a graphic that it's the number of vulnerabilities and what is the CWE. CWE stands for Common Weakness Enumeration, so it's a way to identify a class of issue. I will, in the next slides, show what these numbers mean, because it's pretty hard to to know if you are not, used to this. So you can see in this graph that we have cleared some outliers, and if you are curious to know what they are, here we are. And I bet it's not a surprise for anyone here. So the most common vulnerability that we have are, both classic buffer overflows, and they are followed by other types of, buffer overflows like stack and heap-based overflows. And yeah, that's not at all a surprise. Most projects, using C, they unfortunately suffer from the same problem. So some conclusions about these and possibly some questions as well. So yeah, unsafe, we are using an unsafe program language, right? C, it's very prone to buffer overflows. Even the ones that are not, buffer overflows there, when we are, creating these issues, you can have more than one CWE assigned to them. So sometimes you see, yeah, you have a buffer overflow, and then you have another problem that caused the buffer overflow, that it's an integer overflow or something that you use to do a math that, caused the buffer overflow. And they are, because we don't have many mechanisms to do this in the language. And so, yeah, what is the other conclusion that we have? We have this sort of, lack of awareness about this sort of problem. People think that, only think is in the happy case where everything works well, and they don't tend to think, what could possibly go wrong. And another thing is, and that it's particular to Zephyr, that it's a question that are we, excessively, thinking about optimizations and performance and not caring that much with security. So Zephyr has this whole idea since the beginning that, the application is trusted, everything is trusted unless, it's coming from outside. By outside, I mean something that interfaces with the world. And that it's not as simple as it looks, right? Because sometimes you say, yeah, I have this function that it's really deep into the subsystem. I'm not, directly interface with anything. But end up that, the data that you are getting is also not being checked in the layer above, and you are end up getting, untrusted or tempered data, and you should be checking there. So that it's, something that we really need to review and thinking about. And the other is, so network and Bluetooth, as I mentioned, were the two areas where we got more issues. And there are many reasons for that, right? One thing that I got, talking with some people that reported the issues, they tend to use tools, automated, so fuzzing these, do some sort of black box fuzzing. Network and Bluetooth, it's easier than if you need to do, fuzzing the kernel. Another reason is, as I mentioned, these subsystems are bigger and they have a bigger attack surface, and also they tend to do a lot of parsing and copying buffer from here to there. So that, and as you saw in the previous slide, those are the most common type of issues.
All right. So. I want to talk a little bit about this external code audit that we just did. And so a little bit of background from this. It was 3 years ago? I think so.
Yeah.
There was a company out there, NCC Group, I believe, went off kind of on their own, and they decided to do a code audit of a bunch of pieces of Zephyr. It's kind of one of those, they say open source project, let's show what we can do as kind of an advertisement for their services. And we got this report at the end with, I believe it was like 26 vulnerabilities in it that were found across multiple different kind of subsystems. And that didn't show up on the spike because it was while we were still on Jira, but it, big spike in vulnerabilities that all came in. But there was a lot of things that got fixed as a result of that. So we kind of decided, worked with the governing board, because they're not going to do it again for free. They want money. And do we want them to do it kind of thing. So what is the benefit of an audit like this? You know, we have people looking at it. We have people doing training whose students then are motivated to go look at the code. But what can be gained by a company who's dedicated to looking at this? And there's kind of a nice aspect of this, of having an independent entity looking at it. You know, you have somebody that's not working with Zephyr, because you're familiar with this. You work with code, and you just kind of stop looking at the details, and you just kind of assume that, and it's really easy to miss things. And when somebody comes in who's fresh with this, it gets a set of eyes that can see things that you wouldn't otherwise see. But it has some other benefits there of the idea that we can say, well, we had this audit done, kind of helps with the idea of trust, that, yeah, we're taking this seriously, we are looking for these issues, and we have some things that we're doing about it. In addition, reputation, that kind of thing. So we decided to do this. How do we pick them? And, it kind of comes down to these points here of what is their expertise, what do other people say about them, what's communication going to be like? Because the previous one that we did, they gave us a report at the end, and it would be nice to work with them in the process of this. How much does it cost? We have a finite budget. And just, do they have experience with Zephyr? So we came up with a couple proposals and sent these out to a couple of them. We ended up deciding on NCC Group, the same people that did it the previous time. But we have a limited budget. It's not just them deciding, oh, here's an unlimited amount of time we're going to spend on this. So we wanted to decide to narrow down. And this was mostly a conversation with the board as we're spending a chunk of money, how much can we spend, and where do we want to focus? So there's two aspects. What part of the kernel do you look at, or not the kernel, what part of Zephyr do you look at? Because Zephyr's really big. There's drivers, there's subsystems, there's the kernel, there's libraries, there's all this stuff. What's going to be the most universally beneficial? And you find that drivers are usually focused, they're important, but it's usually a few chips that have that driver, a few chips that have this. Same thing with architectures. That's going to be this architecture. But there's this big thing that's the kernel that everybody uses. The other question is, how deep do you go? When you look at it, is it a bunch of things that we look at in a kind of high-level sense? Well, what about all these interfaces? Or do we take some smaller piece and dive down and look at the whole thing? But the other thing that coming into this is the notion, we have some threat models that have been written, especially some of these things we'll get to in a second, that describe what is our expectation out of security, what is the threats that we are expecting to be attacking. Because it's really important when you do a security analysis, if you don't have an idea of what the threat model is, you can be testing and looking into some part of the code where that doesn't actually matter. That's not a threat that's real in our situation. So what do? We decided to focus around the core kernel features of Zephyr, specifically user mode. So this is if you're not familiar with what this is, it's a separation. Most processors have the notion of user mode. They use random words for it. But the idea of you have kernel or system, and then you have user space. And when you're in user space, there's a lot of things you just can't do. There's memory you can't access. There's registers you can't talk to. And so we make use of this along with memory protection, that certain threads, and you have to make system calls, and they're really specific things that you're allowed to do from user space. And we have a fairly rich threat model written up about this as to what it's supposed to protect, the kind of guarantees that it's expected to provide. In addition to that, there's kind of these mechanisms of scheduling, interprocess communication, those kind of things. And then a bunch of mechanisms that we would call exploit mitigation. So these aren't themselves mechanisms you would really use in your code, but they're things that can be enabled in the system that, if an exploit happens, can limit the scope of harm that is done by that, or what can be done when it's exploited. And some of these examples are things like stack canary, stack guards, stack pointer randomization. I'm not going to go into details as to how all these help because it gets really, really complicated as you dig into this. And you know, why does randomizing the stack pointer help you? And why is that hard to do on an embedded system and that kind of thing? So what happened? We went with the NCC group. We decided to target, so we call that, we started with 3.6 and then there was a 3.7 release, and it was done during this time issue. And they worked on this, I believe it was 6 weeks, if I remember the amount of time that they had with it. And they came back with basically 3 issues. There were 2 of them that we described as low severity, roughly about an integer overflow kind of issue, and the talk tau thing, which is where you check something and then later you use it, except it's changed between when you checked it and when you used it. And then there was an informational one caused by an integer overflow. That one was interesting because it's a real bug in the code. It was a real integer overflow. You would allocate something and you would get back much smaller than, if you asked for this number with lots of 1s in it, you'd get back an allocation that was much smaller. But we got lucky because the application never used the count. It only used the pointer, the size, the computed size. And so there was nothing to exploit, but it was a real bug and it could get worse, so it should be fixed. Am I doing this, or?
I can do it.
Okay, so Flavio's going to go back and.
Yeah, so let's talk about some lessons that we learned from this audit. The first thing is defining the scope. It's hard, right? We have a lot of constraints. There is the time constraint, how long this is going to take. There is, what is the expertise from the auditor? And there are, some time that learning Zephyr by its own, it's a steep curve. So it's hard to pick someone that, never have worked with the project and starting, auditing and looking the code and looking as deep as we were asking. So that was really complicated. And also there is also the financial. These things can go really crazy, price-wise in talking. So we have to put all these constraints that it's tough. The other was mentioned, and it's how deep you want to go. So do you prefer, go and cover a large area, increase the surface, but not go as deep, in the evaluation, or you want to focus in one particular component, one particular area, and ensure that, you have covered well that thing. The other thing is, we don't want to do, an auditing something that will change the next quarter, right? You wanted to make us future proof as possible. So something that, that will be used for a long period. So ensure that the work remains, that was done, remains relevant over time, that it's important. And last but not least, it's hard to get these stakeholder agreement, right? And you have a lot of people with different interests, different, perspective of what should be tested, what should be covered, what it's used for one. It's not exactly the same thing that it's used for others. So come up with these things that, it's useful for everyone, that everyone agrees with, that it's not that easy. The other lesson that, we learned is threat model is really worth, it helps a lot when you are looking for this type of service. It helps you, guide the auditor, so they ensure that you and the auditor are talking the same thing, that you are not, wasting time, that he is looking for the things that, you have already identified as problem. Obviously, there are some rooms to point different perspectives and things, but the general idea is the threat model is pretty good because facilitate this communication and helps to ensure that you both are looking for the same thing. And last but not least, having a good, a comprehensive test, it's pretty good because you ensure that not only you are testing the right thing, that you are, improving your quality, but also helps the auditor, to tweak the test or to see what it's covered, what it's not covered, and it gives something to start. So, what is the next step, right? What is we got this report, we have this experience, what are the next step? What is the strategies, how we enhance Zephyr? So the first thing is we identify that most of the problems comes from, the language that we are using. There are some common patterns and some problems that it's hard to work around. They boil down mostly, to program correctly. So training, in this area, it's pretty important. So we have talked with one, there is this training called Open Security Training. It's good, it's open source, it's open to everyone. One of the guys that have done this course was responsible to find a lot of vulnerabilities on Zephyr that were reported, the one that I mentioned before. So we talked with the person responsible for this course. He thought was a good idea, to provide this to Zephyr. So it's linked in our documentation. We have, we are recommending this for people that are contributing to Zephyr, and we are working with the, the responsibles for this course for in the next, versions of the course. In the updated versions, also we'll cover some of the problems that were found on Zephyr. So because there are a section, specialized for embedded systems and these sort of problems, and they had, some examples and some past vulnerabilities that are used to, to teach. And they were mostly based on Linux and other, systems. And for the next version, these samples would be updated and will contain Zephyr as well. Another thing is, a lot of these issues could be cached by, static analysis tools. So some of them, obviously, no, because you have a lot of indirections from pointers or, casts for types, and the tool is not able to, to go and follow this flow. But some of them were pretty, straightforward to check. So I was, why we are still, facing these problems, and I tested with, some analysis tool, static analysis tools, and all of them catch some of these vulnerabilities that were reported. So we make this mandatory on Zephyr. We define, a cadence to run static analysis. We defined the process. Now it's part of, our general process. And hopefully this will help us to, to prevent some of these problems. And the other one is community engagement, right? We want to get as much reports as possible. We want people to test Zephyr, to find issues, to report bugs. So there are, universities, people, researchers that, publish vulnerabilities in the past. We are asking them to continue to do this. There are, some of these people, usually they report, the reports that they do, it's not, their main goal. They are working in some sort of tool and just happen to, to use Zephyr as input for the tool to validate the tool. So we want that continues to happen. So when we talk with them, we ask, yeah, continue, please, that it's important. So now let's jump to some conclusions. So yeah, after this out, we have enhanced security, right? They didn't find a lot of issues, but they found. So that it's the most obvious. We fixed this problem, so it's a little bit more secure now. The other thing is we have now increased confidence, right? They are not part of our community. They were paid, to do this, to find the issues, and they found only these 3 minor issues. So somehow this brings some sort of confidence. And the recommendations that came from this report were pretty aligned with what we have discussed in the past that we were planning to do. So obviously they said, yeah, you should be fuzzing because that it's it's a good way to catch. It's a good practice. So that was something that we have discussed in the past. Obviously, there are some complications. It's not that easy to fuzz microcontrollers and kernels. So, but that was aligned with who we were planning. And yeah, so these are the statements that came from the report. So they appraise the quality of the kernel in general and how it's being tested. So that is reassuring. And now we are open for questions.
So around the CVEs, the counts that you've got there, are they only for things that were initially reported as a CVE and subsequently fixed, or does that include some number of like just serendipitous pull requests that fixed the bug and someone recognized as, oh, this is a security issue? And is there like any way of, or any ideas around tracking just general bug fixes and assigning those to CVEs? Because it sounds like a hard problem, because obviously bug fixes can be related.
So, I mean, one of the things that's always challenging as an open source project, we don't have a mechanism to go fix CVEs in secret. And I know the Linux kernel dealt with this a lot of, bug fixes kind of become regular pull requests that you just don't talk about the security aspect of it and hope nobody notices before the embargo period. I don't know, do you have statistics on what things were started as CVEs versus, because I don't remember creating, there's not a significant number of CVEs that were created from pull requests. It's mostly been things reported and then fixed. To answer that part of the question.
Is that because you think that doesn't happen very often, like random pull requests don't normally fix CVEs, or you just think it's
I think we don't notice them. There's nothing to tell us that there's probably a lot of pull requests that fix things that possibly could be exploited, and no real obvious way to know that that's what those are. There's a lot of pull requests. Zephyr is very active, and we don't watch all of them. Sorry.
As an application developer that is really interested in security, is there any document describing hardening techniques or things I should be doing? For example, you mentioned stack canaries. Is there any place where you describe best practices?
Yeah, we have a session reserved for security in general. So we have this all documented there. There are some best practices or information about the process on the project itself, but also how to use these features. There is a threat model that it's open as well, the one that we use it to do the audit. It's there, it's documented. And we have also tools. There is one tool that we borrow from Linux basically and adapted to Zephyr that checks what is your configurations, which options you are using in your application, and give you some recommendations. Say, oh yeah, you're using this option, but this option is not secure. This can, be introducing some problems in your application, or oh, this feature that you are using is unstable, or be aware of this. So this tool is also available and documented in the project.
Thank you.
So have you seen so far any practical exploits that would be created based on the security vulnerabilities published that would, lead to some of the breaches in the threat model?
Yeah, some of the reports come with, a proof of concept, so a way to exploit the issue. When we publish, the CVE and do the disclosure of the information, we don't put this there, we don't make this public, but some of them definitely can be easily exploitable. And others, they are more speculative and say, oh yeah, I know that this can be a problem, but I'm not sure how to exploit this, because create the exploit itself, sometimes it's much more complicated than find the issue. But some of them, for sure, we know there are ways to.
So it depends on which question you're asking, because if you're asking, are we aware of any exploits that happened in the wild because of something in Zephyr, and I'm not aware of any of those. We have these kind of white hat type of exploits that are given, but I don't have visibility, at least, into something where an exploit was used for something in a device.
Yeah.
So the code that has been analyzed, the kernel code, is portable code, platform independent. Some of the mitigations that you mentioned, like stack pointer randomization, is probably also platform independent. Stack canaries, to my knowledge, are a compiler feature and mostly widely available as well. Are you eventually going to go one level to the next lower level of mitigations, which are platform dependent, like MPUs, MMUs, because there might be bugs in that code as well? So if you say, like, when you're talking about user space, such MMU, MPU probably come into play, and there might be implementation bugs there as well, which result in security vulnerabilities. So are you eventually going to go that one level lower?
Yeah, so the first out that happened, that was mentioned, one of the issues that were found was in the ARM MPU implementation. So it was fixed there. And I believe that was also affecting ARC MPU. But yeah, when this comes, at this point, most of the tests or the work was done on top of QEMU that simulate x86 with MMU. But any of these problems that were reported, went to that point, was in a layer above. And when talking about the architecture, yeah, for instance, not only about MMU, MPU, but the x86, for instance, have a series of fixes for speculative and issues that are affecting only that platform. So we go this way down.
So one of the challenges with that is, the budget comes from a governing board, which consists of a representative or two at most from each of these member companies. And as you start getting architecture specific, it starts to vary, because you have something like ARM where that's a good chunk of the architectures, and maybe that's enough to vote into, looking into that. And then you have, an architecture that's just one member, and that's a little hard. So it's hard to say where we're going to be able to go with that as far as looking into it, because I know there's some concerns like I have with some of these MPUs have really significant constraints on what's allowed. And QEMU doesn't check that. And so everything can appear to work just fine, and there may be something exploitable there. And no, we haven't looked into much of that at all yet. And I don't know where that will come, but it's important. It definitely is important. Maybe we need to get some kind of mechanism where there can be stuff done for one architecture that the participants from that architecture are interested in, kind of thing. So, good question, though.
Hey, so yeah, I mean, I'm aware of many of the static analysis tools that we have, Coverity, and I think Sparse is another one. Is there any other tools where maybe in our code, our C code, right, we could annotate various pointers and buffers and such, where these static analysis tools maybe have more information available to them to then go look, right? Closer to maybe, say, a safe language might have to itself, right?
So I'm not aware of any efforts on that, to do that. One of the problems you mentioned with static analysis in C is very underdefined. It's full of nasal demons, if you've heard that term before, of undefined behavior. And we kind of sometimes push the edges of that because we're doing really low-level stuff. And it means that the static analysis tool, it doesn't necessarily know what is this pointer for, and what is this thing. And there's definitely a lot that can be done. Part of the problem is it's usually specific to that static analysis tool. You can say, like, oh, this piece of data came from the outside world. Be scared of it, and do a deeper analysis based on this assumption that it can give you the balance between getting 100,000 errors out of your static analysis tool and getting a few hundred that are much more likely to be exploits, but it's not something we've explored much yet.
Yeah. So there are some tools that allows you to put some annotations in the code, but the project tries to be as agnostic as possible for tools. So we avoid this kind of thing, and what we are trying is to be generic and then try multiple tools. So there is a framework that generalizes how to do this.
I think that's it for time.
Any more questions? The last one, maybe? No. Okay. Thank you, guys.
Thank you, everyone.
Thank you.
That's it. Once you got green, you can kind of hear my voice already.
Do you hear me? Yeah. Okay, I hear myself.
That's good.
Very loud.
You're fine. You're fine. Out there, it's a lot different.
Okay. Hello, everyone. I'm Juliana. I'm working at NXP. I'm part of the Linux kernel BSP team. I'm working on Linux, mostly audio subsystem, Zephyr, and also sound open firmware. Today, we're going to talk about how to integrate my proprietary code in Zephyr. And the agenda for today, it's the following. So we are going to talk about Zephyr structure to see where we want to integrate proprietary code and where we are allowed to do that, about the license of Zephyr, some information about the requirements of application development and how can we create an application, about out-of-tree device drivers. Next topic would be toolchains, a case study of sound open firmware and its integration with Zephyr, and at the end, we're going to draw some conclusions. So let's see. Zephyr project is based on West tool. Zephyr folder, the last one here, it's the main manifest repository. It contains the source code of real-time or the Zephyr real-time operating system. The West .west folder contains the West configuration files. And when we initialize a Zephyr workspace, multiple folders are created, like the bootloader there. It's associated with the bootloader used by Zephyr. That's typically MCU boot. We have modules. These are projects that Zephyr relies on. They bring functionality and features that are approved and endorsed by Zephyr Technical Steering Committee. There are multiple categories of modules, including but not limited to debugger integration, silicon vendor hardware abstraction layer, what else? File system, cryptographic libraries, interprocess communication libraries, and more. Optional modules are a subset of the modules above. These are not used by all applications from Zephyr. They are used by some of them, and they are brought in Zephyr based on the specific requirements of an application. So if you want to bring this optional module, you have to do a West config before doing West update. Update populates and fetches all these modules. And then we have tools where we have different tools for testing. On the right side, we have some modules example that can be found in Zephyr project repository, like SDK-ng, where we have the Zephyr SDK, and which contains the toolchain and some development tools. The cross-tool-ng is used to build the toolchains. Docker image provides a Docker image for Zephyr development and testing. We have there some examples. CMSIS DSP and CMSIS NN are optimized library used for computation and neural network. OpenAMP, LibMetal are examples for interprocess communication. LittleFS, it's an example of a fail-safe file system designed for MCUs. And there are more, others. Now, the Zephyr repository we have there on the right, it's well organized to facilitate development. We have there a high-level overview of its structure. We have architecture-specific files in the Arch, board configuration files in boards, build files in CMake, driver code. In DTS, we have device tree files where we define non-discoverable hardware for specific boards. In kernel, we have architecture-independent kernel code. In lib, we have library code like the minimal standard C library. A lot of samples in Zephyr to demonstrate the features of Zephyr. In stock, we have system-on-chip files. In some manifest, we added there the optional modules, tests, a lot of tests. And in addition to all these folders here, we have configurations and build files like kconfig, CMake list, and the main manifest, that's the West YML. Now, about the license. So Zephyr is Apache 2.0 licensed. It's a permissive and easy to understand license. It's widely used in the world of IoT. But it also uses and imports some scripts or packages that are GPL v2. Also, very important, For Zephyr, it's very important to follow the developer certificate of origin process. That means that when you have a contribution, by adding your sign of buy on your patch, you agree with this DCO. And also each file, each source code file from Zephyr has an SPDX license identifier, which clearly states the license of that file. If we want to import code in Zephyr, which is not Apache 2.0, well, in this case, there are additional steps to be followed. Usually this code needs to be approved by a Zephyr Technical Steering Committee or even by the governing board. And this flowchart shows the process of this. I'm not going to enter into details, but there are a lot of steps to follow in order to be approved. Okay, let's see some prerequisites of creating an application, of application development. So usually the Arch support is mandatory to be in Zephyr. We also expect for the board or SOC or device tree to be there, but they can also be out of tree. In case they are out of tree, it's very important for the board and SOC to have the exact structure as in Zephyr. So on the right side, we have a board structure. There are multiple files that can be found there, but only the blue ones are important. So in the board YML, we add the name of the board, the SOCs and variants of that board. In kconfig, we specify settings that are specific for that particular board, settings like board's hardware layout, memory size, or some peripheral configurations. And for the DTS, we add their information regarding some SOCs, about the SOCs of the board, about connectors or other hardware components, like, I don't know, LEDs, buttons, or other connectors. So if we have an out-of-tree board or SOC or DTS, we can give that just as a CMake variables when building the application with West-build. Now, another important prerequisite it's to be followed is the build system of Zephyr, which is based on CMake, and this is application-centric. That means that it requires that the Zephyr-based application to initiate the build of Zephyr code. The application build controls the it initiates actually the building of Zephyr code, and it compiles them into one single binary file. The files in the application directory link Zephyr and any modules with the application itself. On the right there, we have a structure of an application. The most important files there are the CMake list. That's the file that is used to combine our application with the CMake build system from Zephyr. And it's also used to tell the build system what other files are used for our application. And of course, the C code, the source code, which can be found in the SRC folder. In order to integrate external code, there are two main options. So we can integrate them directly in the Zephyr repository. That's by importing the source code into Zephyr. So, but here we have to follow some requirements from Zephyr. That is the license, the coding style, the static analysis. The second options will be to import parts of a whole third-party open source project into a separate repository and integrate it with Zephyr as a module. Okay, so modules, I've talked about a bit earlier. There are, modules are limited to, okay, actually let's take these three options of modules, and we'll see which one it's best for a particular case. So we have to pay attention which kind of modules we use and where do we integrate it. So if we want to add modules in the main manifest file, in the WES-YML, these are limited to modules, to projects that are used by Zephyr subsystem, like, I don't know, libraries, by a platform, by hardware abstraction, like hardware abstraction layer, where we have the drivers for a particular vendor, silicon vendor. We have tools that are used to build and test Zephyr components. Now, optional module, we can integrate optional module. This should be standalone projects that have no dependencies or on any other project from Zephyr, and they are added in a special YML file. And then we have the external modules. These are not in the manifest of Zephyr. They are out of tree, and we provide only documentation on how a user or developer can activate their functionality. Okay, now it's the main topic of our presentation on how can we create an application. But first, let's see what type of application can we do. So there are three main applications. We can, based on the location of our application, we can have repository application that's in a West workspace, and it's in Zephyr repository. Next, we have a workspace. That means that it's outside of Zephyr repository, but in a Zephyr workspace. And the last one is a freestanding application. It's outside of our workspace. On the next few slides, I'm going to show you an application I've created, and we're going to move that application from repository to a freestanding application to see what changes we have to do for these cases. We're not going to talk about workspace because it's very similar with the first one, and there are not much. Actually, there are no changes to make. I will explain later what changes might be possible, but it's very similar with the first one. Okay, so I've created an application, a number crunching sample. It does some vector operation, fast Fourier transformation, and filtering. This application will be moved in and out of tree to see what changes. To demonstrate how to integrate proprietary code, I've used the nature DSP library from Cadence, which is in an out-of-tree location because it has a proprietary license. And by default, this sample is using CMSIS DSP, which is in Zephyr as a module. Okay, this is the structure of my application. Important files are in SRC folder. So the main, we do the operations. In MathOps, I've created a common API for the two, for CMSIS DSP and Nature DSP. And the specific API is called in their specific wrapper. Okay, in order to link our application to Zephyr CMake build system and with the out-of-tree library, we need to have some specific CMake commands in CMake list file. So let's see. In the first part, we specify the source code and include directory. Now comes the interesting part. Next, we define an environmental variable. I called it lib location. And based on this, we select the backend. With the add subdirectory CMake command, we add the external location of our library. Using link libraries, we link with the external library, and we include directory. Now, on my external lib location, I have the library, I have the headers, and the CMake list file. In this CMake list, I'm just setting 3 variables. So lib location, lib name, and include directory. These are used on the application side, as you've seen earlier, to link with the library and to include directories. Now, we can make some changes. We can move the part of link library and include directory from the application in the external lib location, or as you can see in this example, or we can use a CMake variable rather than an environmental variable. Let's see what changes, why would you do those changes? There's not much of a difference. Difference is in the build command. So when we build the application, I don't know if you pay attention, but this was a repository sample, repository application, because it was located in Zephyr repository. So to build it, we use West build. We give the name of our board and the path to the application. So in this case, if we use an environmental variable to set the location of our nature DSP library, we need to set it before building the application. Otherwise, the CMC's DSP backend will be used. If we use a CMake variable, we just pass it when building the application. With, as you can see here as the second example, with -d lib location. Now, the second solution of how can we integrate our external code in Zephyr. This is the Zephyr way, I call it. That means that we are using the external module mechanism from Zephyr. For this, we need to add the Zephyr extra module CMake variable when building the application. This CMake variable, it's already used by by Zephyr CMake build system. So we just pass it when building the application. Now, in this case, our external lib location is seen as an external module. So to be an external module, we need to have in Zephyr a special structure. So we need to have this Zephyr folder in our external module with this module YML file. Here in the YML file, we need to specify the name of our external module, because this will be used when building the application. It refers to this sample, to this external module when building it. And also, next with CMake, we specify the location of our build file, our CMake list file. In our case, it's in the root folder of our external module. And next, we define a blob. Let's see what's a blob. Okay, so with this solution, we use binary blobs to build with our external lib location. So what is a binary blob? A binary blob, it's proprietary machine code and data built in a binary file, and its source code is not released under an open source initiative license. Zephyr can download and use the binary blobs via its built-in system mechanism, actually. And yeah, that's about it. Actually about binary blobs. But in order to use these binary blobs, we have to specify the blob section in modules YML with those entries there. So we have the path where the binary blob will be downloaded relative to our external module. We have a SHA. This is used to verify that the binary blob is valid. We have the type. There are two types supported right now in Zephyr. Okay, the version, the license path is very important. We have to have a license for that binary blob. The binary blob, it usually has a proprietary license, and we need to have that. The URL, it's the location where the binary blob will be fetched from. Description, a human-readable description of the blob, and the doc URL contains the documentation about that binary blob. How can you use it, and how to enable its functionality. This binary blob, it's fetched using West blob command, and very important, this command only fetches the binary blob. So if you need any other accompanying code, like the headers, they are not brought with the binary blob, only that blob. So we need to have the headers, in our case, in the external module. Let's see what changes. So in the CMake list file, do you observe something? Not much, I'm telling you. So we just include directory, and we link with our external library, which right now actually is a blob. It's called a blob, but it's still that library. Now, on the application side, we are checking for the Zephyr extra module variable. If it's defined, okay, we're selecting the nature DSP backend. Otherwise, the CMSIS DSP will be used. Let's see what changes if we move our application from Zephyr outside of tree. It will be a freestanding application, if you remember. So actually, everything applies as before. Just the build commands will change a bit. If we are building from a Zephyr workspace, we use the west build command. We give the absolute path or the relative path to the application. And in Zephyr, we get the build folder. I was mentioning before that I will not talk about the workspace application, but while I'm here, I will tell you that it's not much of a difference, because if we have the application in another place, also in the Zephyr workspace, we just give that path to relative to our project, to our Zephyr workspace. So that's why I'm saying it's not much of a difference. Now, if we are building the application outside Zephyr workspace, we are going to use CMake and Ninja. This is a three-step process. We'll set the Zephyr location, we'll use CMake to get the build folder, and use Ninja to compile the code. So first, we need to set Zephyr base. This is an environmental variable where we set the location of our Zephyr workspace. This ensures that the CMake can automatically select a Zephyr installation to use for building our application. Second step will be to use CMake to generate the Ninja-based system build. And we get the build folder there in our application. In this case, now we have in the build, we have the Ninja build file and other generated build files. And finally, we use Ninja to compile the code, and we get our ELF in the build folder in the directory, in our application directory. Okay, another use case is a custom workspace. That means that for a custom workspace, we'll need to have a specific manifest. That means a specific West YML for our application. So in this contains a description of Zephyr installation, including Git repository, and the necessary dependencies of our application. So this is an example of how our West YML will look like for this particular sample. So we only need the CMSIS DSP, the Extensa HAL and NXP HAL, and we are going to mention this using name allow list. And for the Zephyr repository, we're going to use main branch. So that's about it. Why should I bring all the dependencies from Zephyr if I need only these? So I'll create my own West YML. Next, when building the application, after we initialize the workspace, we use West update to populate the workspace, so only the needed dependencies are brought there. And next, we can build the application as before, West build and the application. And yeah, that's about it. That's about it about an application. We can also have out-of-tree device drivers. And I have there on the right source code of a proof of concept of an interrupt, interrupt controller for RQSteer. RQSteer is an interrupt controller on the DSP subsystem of i.MX 810+. We know its base address. We know the interrupt number. We use Zephyr API, interrupt API, to enable the interrupt and to register the handler. And what we do is just trigger an interrupt to test the ISR is called. And you can see here on the left that our interrupt is triggered. That's the console output. Of course, this device driver, this proof of concept device driver can be improved and can be enhanced to be as Zephyr, as a Zephyr device driver, we can take the interrupt number or the base address from DTS. We can interface it with the interrupt management subsystem from Zephyr. And also we can integrate it with the build infrastructure. Okay, next topic is toolchain. Zephyr SDK contains toolchains for each Zephyr supported architecture. It's recommended to be used, and in some condition this is required, like in continuous integration. But you can also use some custom toolchains. For that, you need to define two environmental variables, Zephyr toolchain variant, that's the toolchain name, and toolchain root, the path to the directory where we have the toolchain's CMake configuration file. We can set this environmental variable, or we can pass them directly when building our application with West Build or with CMake, as you can see here in these two examples. Next, we are going to talk about SoundOpen firmware and its integration with Zephyr. Okay, a little bit about SoundOpen firmware. It's an open source audio DSP firmware and SDK. Has its own repository, its own lifecycle, CI, tools, and everything. It's BSD3 closed licensed, but also has some device drivers that are BSD and or GPL. So SoundOpen firmware started as a standalone project, no Zephyr relationship whatsoever. It was using Extensa OS and its own device drivers. So later on, SoundOpen firmware technical steering committee decided to switch from Extensa OS to Zephyr. Once the Extensa architecture was added in Zephyr, we only had to add the board support. This is something I've done 3 years ago. I've added the support for the audio DSP subsystem on i.MX8 family, and I ported to hardware model 2 a few months back. And at that point, SoundOpen firmware was an out-of-tree application that was using only the Zephyr Kellner API. The platform drivers were still in SOF, like my proof of concept device driver I showed you earlier. Now we are porting the platform driver from SOF to Zephyr. So SoundOpen firmware will use not just the kernel API, but also the device drivers API from Zephyr. And also SoundOpen firmware was accepted as an optional Zephyr module. So I've showed you this because you can start from a standalone application, which is not a small application, it's a firmware, and you can port it to Zephyr or use some parts of Zephyr. So, okay, let's make a summary now. Zephyr build system is very powerful. You can do the same thing in multiple ways. You can create an application in and out of tree. You can link it with an external library using external modules or not. You can use binary blobs for an external library or not. You can also have device drivers that are out of tree, but you can also have SOC or board or device trees. So there are extensive documentation and samples, including mine in Zephyr, as a starting point that can be used as a starting point. Just you need to pay attention to the license, as in any other project. So thank you.
Okay, we have some time for questions, if anybody has any questions.
Hi, just one question about this out-of-tree build. As I understand, we still need to modify Zephyr itself, to modify with some modules YAML to have this downloading working, right? Or I missed something?
That module's YML, you add it in your external module. You don't have to modify anything from Zephyr source code. You have it in your external module, you put it there, and you modify it as you want. Well, you have to follow some rules for that, but you're not modifying source code in Zephyr or any other configuration file. It's in your external code.
Okay, thanks.
module actually.
Okay. Any more?
So do you have it on the roadmap to convert the sound open firmware drivers over to Zephyr? When's that going to happen?
Well, it's ongoing. This is ongoing. We already done for some of them, and I think we have 1 or 2 PRs open right now. But it's working pretty well. It will be done. It will be finished soon.
Okay. Any more questions? I think that's it then. Thank you, Juliana.
Thank you. Did I spoke too fast?
All right, I think we can slowly get started. My name is Benjamin Cabé. I am a developer advocate at the Linux Foundation for the Zephyr project. And today we're going to talk about SBOM, software bill of materials, what it is, how you can use them with Zephyr. Being a developer advocate, I guess, I'm by no means a lawyer, by no means an expert on the topic of like software supply chain management, but that's almost kind of the point of the presentation. We hear a lot these days about like software, like tracking software provenance and those kind of things. This is becoming increasingly important, especially in the context of embedded devices. And I wanted to learn more, quite frankly, about the topic, figure out what sort of the landscape of the tools that are available out there to help with that, basically. And by that, I mean, what is an SBOM in the first place, why you should care, what makes it even more important to have a sense of, like, what is your bill of material software-wise when it comes to embedded, what are some of the tools, standards out there, SPDX is one that you may have heard of. What does it mean for Zephyr? Like, are there things available that can help sort of capture the SBOM, and we will see what an SBOM is in the first place. What are some of the tools, and hopefully some time for Q&A as well. I mean, some of you, many of you, most of you, I don't know, you are embedded developers one way or the other. A BOM you're familiar with, sort of like tracking and capturing the list of all the things that physically end up making up your PCB and your actual device. That's great, and I mean, you need that. And I mean, actually some regulation authorities might actually be interested in that. Kind of similarly, frankly, you want that for your software as well. This sort of like nutrition facts kind of label and list of what are all the things that I'm pulling when I'm running West build for my Zephyr application, what ends up being shipped, being put in the ceilings of whatever buildings where I'm deploying remote and like wireless thermostats, what is ending up in cars, medical devices and whatnot. Like, it's important for many reasons which we will dive into, but they all point down to understanding basically what is the kind of software that you're sourcing and shipping into your actual products, and basically managing your supply chain for the software as well. There's many reasons why you need to basically extend the and to look into what kind of software you're shipping. It kind of starts with, frankly, for legal reasons and licensing reasons. Like, you might not be able to use necessarily all the kind of software that you wish. Like, there might be some open source software, open source projects out there that you would love to use, but they are basically just incompatible with either other open source software that you're already using, or just incompatible with your product strategy or your company's policy. So basically helping you understand what it is that you're pulling when you're sourcing open source component A, what are all of the other dependencies that are not necessarily super visible at first, so that you can realize that, oh yeah, I thought A was okay, but there is this dependency that will actually be problematic. Or also, decision-making wise, having more visibility into your sort of dependency graph will also help you maybe design your software better, because you will sort of think twice when it comes to just like very conveniently taking this random project off of GitHub and figuring out that at the end of the day, although the license was kind of okay, it kind of pulled many other dependencies that might sort of bite you later on. So getting more visibility, more insights into the kind of things that you will be sourcing and eventually putting in your final image is quite important. Frankly, there's also reasons that are basically this: you're shipping a product and the FCC or the Cyber Resiliency Act in Europe, and whatever new regulations might come, existing or new regulations, actually ask you, although it might not be like required that you make that available publicly to your end customers, they might ask you that you actually keep track somewhere in your technical documentation of a high-level list of what are the components, what are the suppliers of the software components that you ended up putting into your product. Of course, one other important aspect is you want to know what software you're using, also to get better visibility in terms of, am I impacted by a security vulnerability? I mean, I kind of know that I've been using embed TLS, say, for like securing my networking stack. There's apparently a vulnerability in version XYZ. What's the version I was using again in this product I shipped 18 months ago? Hopefully, I mean, it might be, depending on how you've been sort of, what are your internal processes, it might not be that easy to get that information quickly so that you can really react and potentially patch your devices, etc. if you're impacted. If you're not, you also want to know that because you don't want to patch and roll out like painful, risky software updates in the field if you weren't impacted in the first place. And this kind of also boils down to having and using, hopefully, not only like thinking about materializing this software bill of material, but also doing so using existing tools and standards so that you can really streamline the process, and it's not only, it doesn't become an afterthought, but it's really something that just like taps right into your development best practices, taps into like, or hopefully using standards, also taps into other tools that the software regulation authorities and the government regulation authorities and whatnot might require you to produce. Like when you're expected to give an SBOM to, again, say FCC or the European Commission, they will ask for a given set of information. You'd rather use standard tools for that. SBOMs, so it's not necessarily a new thing, obviously, but interestingly, when it comes to embedded, there are things that make it even more important / tricky to address. Like in embedded, I mean, and I guess in many other places, but in embedded, there's often like a really good mix of open source and proprietary software. So tracking and sort of identifying what is what can be quite important. The way to build embedded software, there's actually many ways to do so, and there might be different pieces of your application that are built in different ways. So all those different pieces and compilers and tool chains and whatnot, like, are they able to give you the information, the metadata you need to really capture like all the things that you would hope to get into your SBOM? There's all the constraints around longevity, like embedded products, connected products, IoT products. They get deployed and run for a long time, which means that this particular SBOM that captures which version of embed TLS you were using and which tools, which compilers you were using to build your solution. It's really, really important to get accurate information and across the entire supply chain, which is, if we think Zephyr, but really any embedded project, really, there's lots of pieces, lots of software components that you're pulling, right? Like there's probably HALs from your silicon vendors, there's the RTOS bits, there's third-party modules, like I mentioned, embed TLS, could be TensorFlow Lite, I mean, you name it. There's your own code, right? Like it might be released under whatever license. It might be, yeah, whatever, really. But yeah, it can be complex. So there's a need to, I mean, and there are standards, hopefully, out there to sort of standardize what should go into an SBOM, what's sort of like the minimal required set of things, and again, metadata that you need to capture to identify the provenance of your software, all things licensing, security informations, like things that identify the software components in a good enough fashion so that you know whether such or such module when there is a CVE reported. Is this the actual module that you're shipping, or a version that is impacted by a said vulnerability? So yeah, SPDX is effectively an ISO standard. If you're familiar with the topic, at least remotely, you may have seen that there is a brand new version of SPDX that was released over the weekend, I think, and we will be briefly touching upon that. What is SPDX? How does it look like? SPDX, it should really say up there. So you will see the typo for the next couple of slides, I guess. So it's, you may have heard the term, frankly, just because you're a contributor to open source, and there's always those headers, copyright headers or license headers that mention the standard. There's more things that go into the standard in the form of basically standardizing a manifest for, say, if I were to build this open source or whatever, really, this application made of really only a simple source file, a make file that provides probably some kind of instructions to build the system, and then a binary with SPDX, and without like, we won't read everything line per line, but splitting all the entire content of like the manifest for the hello package / application that eventually might go into an actual product would look something along those lines. Like you would have a set of like keys and values that go into the file, identifying who created the package in the first place, who created the manifest also. It might be you might have been relying on a third-party tool to help you with providing some of the information in there. Where can one find, like, where's sort of the origin of the software, of this particular software package? In this case, looks like it comes from GitHub. What is the SHA of the commit corresponding to the version of the application / package? What's the license that is provided by the provider of the package, either through like documentation, or either through, it might be something that the tool has automatically guessed based on other information. So this is something that can be materialized in the SPDX file. What is the actual binary corresponding to the application? Again, it probably has some kind of hash and signature that can prove useful to check later that the package hasn't been tampered with. What are the source files? What is the license, the copyright information of the source file? I think you get the idea, right? Capturing also the relationship between all those elements. The source file gets touched and gets manipulated through the make file, so that it eventually generates a binary. I mean, all those kind of dependencies. Again, you get the idea. This is how you're eventually going to capture the kind of information that will be useful to know. Oh yeah, like someone just told me that this source file in embed TLS in version XYZ is problematic. Is it part of my build? Is it part of my package? You can get that kind of information. How do you build the SPDX file? There's tools out there, and it can be, some of it may be done manually. I don't think that makes sense when it's like, when we're talking like hundreds of compilation units and tons of like license information, etc. So obviously there's tools that help automating that. In the context of Zephyr, actually, there is a support for SPDX. Not SPDX 3 just yet, so we're looking and talking about SPDX 2.3 at the moment. But the way it works is pretty simple. As an end user or a consumer of this functionality, you just ask West, the West meta tool, to generate an SPDX for you. And so it's kind of like a three-stage process. First, when initializing prior to building, you sort of want to give a hint to West and to CMake under the hood that you want to instrument your build. So the reason it's opt-in is basically because it might slow down your build just a little bit. It's basically going to use CMake API. Like, we are telling CMake ahead of time, I want you to give me lots of information with regards to what are all the compilation units that are going to be pulled into my build, what are their dependencies, whether they come from Git or something else. I mean, there's quite a nice API actually that West is going to use or is going to tell CMake to enable. Then we build the project as usual, with, again, an extra option that gives even more metadata to capture even more metadata. I guess, actually, I just said something wrong just before. For example, identifying whether something comes from Git or not, this wouldn't be CMake that does that. This is actually West. So enabling the build output meta thingy, this is the kind of thing you need to know what are the modules that your application might be using. Modules as in Zephyr modules. Zephyr modules potentially mapping to modules in the context of CVEs. Like CVEs are reported against embed TLS, against tiny DTLS, whatever. And so once we have basically our build, all our artifacts, plus all the metadata, then we can just compute and spit out an SBOM. 3, actually. 3 and soon 4. It's the way, I mean, yeah, it's split across 3 files, but essentially this is sort of the same information that you get. In one file, you would get all the, something that's more like related to the actual sources of Zephyr, and the one out of the thousands and thousands of files that make up Zephyr, there's probably only a handful or maybe 100, I don't know, but not only a few that are going to end up linked into your final binary. So what are those sources? What are the file names against, again, the MD5 hash, etc. So the Zephyr.spdx file captures that. The app.spdx does about the same, but for your actual main and your own application code. And then the build SPDX is more about the build artifacts, like the final health image, potentially the .a's and sort of like the all the intermediary objects that were built. And again, with all the dependencies, allowing you to track how such or such library or such or such final image was obtained. And so, yeah, that's what you can get for free, basically, in Zephyr. And we're going to see sort of in action what is the information that's captured and how to make sense of it, because, I mean, that's what you want. There's many things that the SPDX prove useful for. First one, I guess, is if you start caring or being asked about having SBOMs, you better do it in a way that, like, where you're actually capturing as much information as you can. Like, it won't help you all that much if the SBOM only tells you the list of all the files that were used for building your application. Sure, it will be still sort of a valid SBOM, but if it doesn't contain like the signature of the files, like the creation date, the origin, as in which repo they were pulled from, etc., then that's not really useful for security management or for anything really. So you want like tools that hopefully help you do that, sort of assess whether your SBOMs are as good as it gets. You want to use the SBOMs, of course, to understand the licenses and what is sort of like your security posture, or I should say, I guess, legal posture when it comes to am I pulling GPL code that I didn't realize I was, things like that. And eventually, or at least on top of that, having the ability to find vulnerabilities, because if you've captured enough information, then you can probably know whether when a new CVE is open, whether it sort of matches the kind of information that's in your SBOM. So some of the tools, and that was sort of my long intro into why I wanted to do this talk. I want you to sort of leave the room with some pointers to open source tools that I found pretty useful to make sense out of the SPDX and the SBOMs that you can get out of Zephyr or any other system, really. One is the NTIH checker. So that's kind of going in order of the 3 bullet points you were seeing just before. First, looking about sort of completeness, like am I building SBOMs that capture enough and useful information? So there are guidelines from some authorities out there. One is NTIA. I actually forgot what's behind the acronym, but this tool will tell you for a given SPDX file, essentially, whether you are doing all you could. So if I were to, and this will be my call to action at the end of the presentation, the tool in Zephyr, like the SPDX tooling in Zephyr is not perfect just yet, sometimes because the tool itself could be more complete and more powerful, or sometimes because we just don't have enough metadata. The metadata we would need doesn't exist in the first place. So it's kind of a bit of both. But yeah, say we look at the SPDX file for my Zephyr application. Apparently, I've done the right thing when it comes to capturing the names, the identifiers of the components. But one thing that's missing is having notion of the suppliers. And so I guess for something like embed TLS, the supplier would be, I mean, there's probably some standard way to describe that. It's probably the ARM embed TLS contributors, or like it's probably a pointer to the website of the project. But yeah, I mean, this is apparently information that would be useful to capture. So yeah, this tool is interesting in that regard. Kind of related, the SBOM QS tool, SBOM QS as in SBOM quality score. It allows you to assess the quality of the SBOM and how consumable it is. So it goes actually, I think, slightly further. The previous tool was really about like guidelines and recommendations from the authorities. This one is more about like quality in general, and we see similar information, frankly. Do we have names? Do we have identifiers? But it actually gives you a score. So you get to dig and to surface better. Oh, okay, I forgot, I have only like 95% of the supplier information that was provided. What are the 5% that are missing? Like it's able to provide you with that information, give you the nice scorecard that some project would probably like and want to actually surface in their readmes and whatnot to demonstrate that they've done the right thing. So yeah, that's another tool. This one is kind of like showing it as sort of an anecdote or as an FYI. It's not really going to use the SBOM as in the SBOM of your actual application, like everything I just said before. It's a tool from GitHub that shows you the a SBOM, which rather corresponds to what are the dependencies that are defined or that can be found in your GitHub repo. So for something like Zephyr, there's like lots of lots of Python stuff that we're proving, for example, as part of the build system or of West, documentation build, whatever. Those are things that you may or may not use, but it's good to know and to have like in just one place a list of the provenance, the versions, etc., etc. That's something that maybe you want to capture whenever you do a release. And so this information is available as well. If you use the GitHub CLI, you can run the GH-SBOM command, but that eventually gives you exactly the same as what you get on the, oh, I'm not logged in, it might not work, let's see. Yeah, it depends, yeah, so that would be the kind of information that you see here. It might not be complete, it might not be reflecting the reality of what eventually ends up in anything really, just like some stuff that's part of your infrastructure, and it might make sense to capture that information. Back to the slides. SBOM2 doc, so that's a Python tool, Python helper. This one is quite nice because earlier I was sort of breaking down what goes into an SPDX file, all those key values. It was really flat, right? And it wasn't really surfacing or showing you any form of structure. With the SBOM2 doc tool, you can get a JSON file, a PDF, at Markdown, which is more like the kind of manifest that you would print and give to the authorities as a really like a list of what it is that you're pulling in your system. I think I was running it just before starting the talk. SBOM to doc for Zephyr SPDX. So out of the 3 SBOMs, this is the one that's sort of listing all the sources that made it into my app. My app here is I built the Wi-Fi sample for an ARM board. So we will see a bunch of ARM stuff, like Zephyr ARM Arch stuff. We will see a bunch of drivers for my particular Atmel board. We will see the kernel, libraries, blah, 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 the network subsystem. And so for all those files, we get the information that's coming from the SBOM, the SPDX file. So license, and this is where we can see that some information is actually missing and could be or should be surfaced there. What are some of the packages that that are part of my repo, etc., etc. So that's SBOM to doc. This one is where it gets really interesting. So the demo of this one I will show in just a bit, but it's a tool from Intel that looks more at the 3rd, I think, bullet point in my list before, tracking security vulnerabilities. Once you start capturing the list of files that you're putting into your application with their hash, and also potentially the list of modules, which conveniently, I mean, we have a notion of modules in the Zephyr ecosystem, right? Am I shipping modules that are impacted by a vulnerability? And so that's the tool, and we're going to see how it works. I mean, you can use it with the current version of SPDX tooling in Zephyr. It will give you some level of feedback, but it starts really getting interesting when you look at some work that the community is doing around improving SPDX tooling in Zephyr, specifically around adding support for something that's called CPEs and their sort of counterpart, which is pearls. So it's coming from security authorities and like the authorities managing CVEs and so and whatnot. They have standard ways to describe software packages. Something like ARM embed TLS. If you look, if you Google for all the recent CVEs around, say, embed TLS, those that have been disclosed or those that are still in their embargo for what it's worth, as part of all the metadata, like you will have, of course, the description, you will have the score, like telling you how bad of or how risky or how serious of an issue that is. And one of the metadata is the CPE. That's what sort of uniquely identifies the package and the version/version range of that the vulnerability applies to. So CPEs, the syntax is the first bullet point. There is another variant which is called pearls, which is more where it would be pointing to some kind of source control management URL. But that's essentially the same information. And this PR, which I was hoping would have been merged before this talk, but I'm pretty sure it will be merged imminently, proposes to add support in Zephyr to augment the metadata of Zephyr modules with the kind of information that I was just talking about. So in Zephyr, when you basically install Zephyr and you do the initial like West update thingy, it pulls all the modules that are defined and described in your manifest, and all those modules themselves, they have manifests that describe how to build them, how to configure them. The proposition is to add metadata that indicates, oh yeah, the embed TLS module that Zephyr has, it's effectively embed TLS version XYZ. I mean, the sort of the fork we have in Zephyr is usually like pretty much the upstream equivalent to the upstream project. And so capturing that information so that when you then build your SPDX, you create the SPDX file for your application, there's one additional piece of information that's being surfaced, which is, oh yeah, your application is, this is the Wi-Fi sample from Zephyr, Oh, it does. It pulls in TLS. TLS, as per the West metadata information, is in version 3.5.1 in your shipped binary. Then you can just ask this tool, and by the way, I'm showing an open source tool, but I know for a fact that there are some commercial tools out there that are way more powerful and way more sexy also to some extent, and have way more complete databases of vulnerabilities that you can use, but granted that you have captured the CPE, that's what you can do. And that's like really, I'm running that against the proposed PR. Are there any vulnerabilities in my code? Yep, you're shipping Ember-TLS 3.5.1. There are three vulnerabilities. Some of them seem to actually be reasonably critical. So that's, I think that's where this kind of promise of SBOMs are meant to be the manifest of all the things that end up in your software. That's where it starts really showing its value, right? And something else that's coming, or was just released, like I said, is SPDX 3.0, which the main idea is that, I mean, I've been walking you through some of the data that goes into an SPDX file. It's, as of 2.x, it's pretty flat. It's pretty hard to, if I go back a few slides, basically. The fact that there's some information missing in there, in the current version of the SPDX file that I'm shipping, might not be a problem depending on who you are. Like there's many entities that might be interested in the manifest of a particular binary image or like software. If you're a lawyer, you really don't care all that much as long as the license information is being captured. That's what you're going to care about. If you're someone who is like, I don't know, a release engineer who cares about reproducibility of builds, etc., maybe the kind of metadata that you want to make sure is being captured are things like the like what is capturing the description of what were the artifacts used to actually build the system. So not necessarily the source files, but really more like the make files and the like descriptions of all the compilers, tool chains, and whatnot. So long story short, the idea of SPDX 3.0 is to describe a handful of profiles to cater for like the different kind of consumers or producers, for what it's worth, there might be for an SBOM. Again, if you're a lawyer, if you're interested in all things licensing, then you really care about all things licensing. If you're more you're coming more from a background of, I want to make sure that what we did with AI is like we have been using models that are clear IP-wise, etc. You might care more about some of the metadata that's being introduced by SPDX 3 around all things AI. So yeah, that's basically what I had. As always, help is very much wanted. I don't know much about you guys, but this is where we have time for a quick discussion. If some of you are interested in those in this work around SPDX and SBOMs, SPDX 3 was just released, improving the current tooling that we have in Zephyr so that it's compatible with SPDX 3 would certainly be most welcome. There is, as you saw, still some data that we could capture that we are not, either because the tooling is not complete just yet, or we would just need to add the metadata to whatever files where it's missing at the moment. And yeah, as always, the best way to sort of interact with the community would be GitHub, Discord, to ask any questions you might have or any feedback you might have. But we also have, I think, a few minutes, 5 minutes for questions.
Yes, you got about 5 minutes.
Yeah, cool, perfect.
First, thank you very much.
Thank you.
Do we have any questions?
So all of the tools you've been showing today rely on the presence of SPDX tags, right? Pretty much?
Yes and no. I mean, SPDX tags, if you, like in the Zephyr source code, there's not that many, frankly, right? It's just the license information, copyright information, we're not even using the sort of the standard stuff. It's the licensing information, like I said in the beginning. It's only a subset of the things that you want to do, and the SPDX tags, as you mentioned them, are mostly related to licensing. But there's also more metadata that just like the kind of thing that you want to capture when you build your application, like the hash of the files or the Git remote URLs of all the modules, etc. You don't need anything special except for the tooling that needs to be built to make sure that you turn this information that you were able to compute into and dump it into the SPDX files.
Yes, but I understand that, but what I mean is in terms of licenses or providing a list of licenses that the application uses, one of the tools showed a very nice...
Yes, you rely on tags for that one.
Yes. Is that relying then on the, I don't know if you call it tags, the SPDX line?
Yeah, that relies on the tags, yes.
Okay, all right.
And this is where I think the commercial tools are adding additional value. In SPDX, there's this notion of the concluded license versus whatever is called the other option, which is you always have I mean, sometimes you will have tools that make an educated guess about the license, right. And you can still sometimes override that because you know for a fact that another license applies. Or I guess it would be the other way around. The tag is missing in the file. The concluded license would be none as per the tooling, but then you as a human, you know where this is coming from and you may be able to add this information. But obviously this is way beyond the scope of open source tooling or beyond the scope of what Zephyr provides as infrastructure, right, to help people.
Right, okay, that's the context I wanted to get. Thank you.
Okay. Yeah, there was one here.
There's someone up here first.
I think you answered it in the previous question, but the Zephyr build creates the XPDX files that you can then analyze, and it creates those files by basically text parsing the tags that are embedded in those libraries that it pulls from.
Yes. So when you enable and when you're interested in SPDX output as part of your build artifacts, you first ask CMake basically to give you the list of what are all the files that are actually relevant. And then once you have this list of source files, this is where you scan them for license information. And this is where you use also the CMake metadata to figure out what's the dependency between, oh yeah, this source file ended up being this .a, ended up being part of my ELF file. And so then you have all the pieces that are finally together, yeah.
So does the Zephyr meta SPDX application, can that be abstracted out away from Zephyr and then used for any project that uses CMake?
Yes, there's actually a talk which I think is still applicable, the content of the talk. The person who actually wrote the CMake-based black magic stuff for Zephyr gave a talk at FOSDEM, I think in 2021. So you will find both the slides, the video online, or you can just look at the code in Zephyr, how they used. I had no idea that there is a CMake API, right? And so that's basically what it's using under the hood. So yeah.
Thank you.
Hey, Benjamin. So yesterday, Kate was showing all kinds of SPDX variants, SPDX safety, security, licensing, and a whole lot of other things. Take safety, for example. I mean, she was showing traceability, testing, and so on. What does that mean to us, for example, as a Zephyr project, to actually get to that? Does that mean adding all of this metadata into the files, the relevant files? Or is that something that would be...
I think it's similar to what Carles was saying at the beginning. If adding some kind of metadata, I mean, there's no requirement, as far as I can tell, like the SPDX specification is really just about the final manifest. How you obtain it is up to you. If adding some tags helps you achieve that, then that's great. Typically, the tags that we have in all our headers for license and copyright, that makes our lives easier, so we do that. But if we have other ways to capture requirements, traceability, and whatever else we need. I don't think there is any sort of standard tags to do that. It might be, we might have our own YAML files, which we will run through some generators to speed out the SPDX file. Does that make sense?
No, what I'm trying to get to, I mean, right now we have the license tag, which is basically the minimum that probably SPDX can consume in terms of like, metadata. A lot of things are automatically generated and figured out, like hashes and stuff like that, and that's completely fine. What I'm trying to get actually to something intelligent like traceability. By the way, the echo here is so bad. Yeah.
It's not me.
Yeah. There will be a need to add metadata and identify files and put like all kinds of things. And I'm trying to understand how intrusive that can be the more.
Yeah. I think I get the question. Yeah. And my point is that as far as I can tell, there's no tool that expects anything. There's no tool that will take whatever tags you're thinking of and will do anything magically. We will have to write ad hoc tools to generate the SPDX files anyways. So it's whatever we think is convenient for us to describe the information. Like even like all that I've shown, it's relying on ad hoc so-called ZSPDX tooling in Zephyr itself. Like the SPDX files, we generate them manually. It's not like we would use a tool to be like, hey, here's the Zephyr sources. We have put all the traceability tags. Please give us the SPDX. As far as I know, this kind of tool doesn't exist. So we'll talk more.
Yeah. Okay, any other questions? Thank you very much.
Thank you.
Great. Lights on.
All right, I think it's time to get started. All right, thank you all for coming out today. So this talk is going to be about the testing and emulation environment within Zephyr and how we can accelerate code coverage with something that I'm calling the generic test coupled with emulator backend APIs. So we're going to start off with a quick overview of what the Zephyr emulation system is like, then introduce the generic test and backend emulator API, and then we're going to do sort of a walkthrough of an implementation of that, just so that we can all get very familiar with how to do that, and hopefully we can maybe try that ourselves with a particular sensor or driver that we like to use. So a little bit about myself first. So I'm a firmware engineer at Google working on Chrome OS. So my team does the embedded controller for Chromebook devices. So we're sort of a system management microcontroller that lives on the device and is responsible for managing things like charging, keyboards, sensors, USB power delivery stack, sort of these low-level functionality things in the Chromebook. And we're actually an open source project, so you can feel free to check us out, look at our code. And then over in the public Zephyr world, I contribute to the Zephyr sensor system, and also have worked on testing and Twister. So if you submit a PR to the sensor drivers, there's a good chance I might be one of your reviewers. All right, so let's go ahead and start off with Zephyr emulators. All right, so when we're talking about emulators in this context, we're not exactly going into things like QEMU or hardware emulation. The best description I have for what a Zephyr emulator is would be more like a mock peripheral. So obviously, your embedded application is going to be interacting with a lot of things like GPIO, ADCs, I2C buses. But if you want to be able to compile and test your application on a host PC, obviously we're going to need to substitute that kind of hardware in with something else because it wouldn't be available otherwise. And so Zephyr has this concept of emulators that can stand in for these devices. They are coded in C, and you'd be normally using these in a native POSIX, native SIM test environment. So you can piece together sort of a replica of your hardware in the device tree for your test using these pieces. And it's super powerful for validating your application without having to use real hardware. It's a lot faster to iterate through, and you can also run it in your CI, so you can get automatic regression testing and make sure that nothing you're doing is accidentally breaking something. So the sort of flow when you're doing this is that you would have unit test code up top, and this would be calling into the normal Zephyr APIs. So we're going to focus on sensors today, so we'll call into the sensor API. That interacts with whatever driver that you want to be testing. And then that sensor driver is doing I2C operations, but instead of going out to a chip I2C driver, it's actually talking to a sort of a virtual I2C bus, the I2C emule. And that in turn is talking to a virtual sensor emulator. And so those two parts, the driver under test and the emulator, are kind of what are working together to power that unit test. And the role of the emulator here is basically act like the chip. So it accepts I2C operations, it has an internal register store, can return data that's being read to it, basically act the same way that a normal sensor would. So a lot of the things I'm going to talk about today are applicable to other classes of devices, but for the sake of this talk, we're going to be focusing mostly on these sensor emulators specifically. So if I haven't mentioned already, the testing and emulation is a good thing. So we of course want to provide our users with the most stable and bug-free code possible, right? And so unfortunately we do sometimes run into issues with the sensor drivers, right? And so as a reviewer, I do get to see kind of what kind of bug fixes come through from time to time. And one of the common categories of bugs are things that have to do with sort of range problems on sensors, and also unutilized features. I don't want to called out particular sensors or PRs in this talk, but one kind of problem, just to give you an idea that kind of happens a lot, is somebody will develop a driver for, let's say, a temperature sensor and commit that upstream, and maybe they were using it in like a room setting like this, testing a pretty narrow range of temperatures, and it works perfectly for that application. But when somebody else comes along later down the road, and they want to use this temperature sensor in, like, say, a freezer or a weather station or something where it's being exposed to a much broader range, they'll find that the driver crashes because it's never actually seen a negative number before, or something like this, right? I have also in one case seen a situation where a sensor purported to support operation on I2C and SPI, had dual bus feature, but if you initialize it in the SPI mode, it would actually immediately segfault. And so I might have actually been the first person to run that code, but it was in the tree. And so I think issues like this are an opportunity for improvement. And I think that the emulation and testing combination is a really, really good way to thoroughly test these drivers, work all the different features, get good code coverage, all the branches, and then be able to ship a driver that we are pretty confident in and stable. Now, of course, there is some time investment involved here. And so part of this talk is going to be to propose a system that makes this a little bit easier, but I do think overall that it is worth it. So when we're talking about a typical sensor plus emulator test, this kind of mirrors the slides we were looking at earlier, but we have that test code, right, calling sensor API functionality. So it hits the driver is doing its I2C operations like normal, talking to this emulated sensor. Now, in order to close the loop right here, the test also has to be able to control the emulator, basically set expected values, expected state, so that when we talk to it through the driver, we can actually make sure that it did the thing that we wanted it to. So how does that work? Typically, these emulators will expose some kind of custom API to allow you to configure it into a particular state. So you might have a function like this, where we say set register hex 45 to that ugly hexadecimal number. That would, in this case, be encoding some kind of temperature reading in the native register encoding that driver uses, which is non-standard almost all the time. We then call the API to get a sample using fetch get or whatever, and then we just compare that what we got out from the driver is what we programmed into the emulator to begin with. And so this works pretty well. This basically tests the data path of the sensor. But if you do this a lot, you'll suddenly notice that this one part right here is kind of the only step that's unique to a device, right? If you could have a standardized way of talking to these emulators and let the emulator be in charge of doing that conversion from like a real-world SI number into a register representation, then the test could suddenly be like reusable. And that's what we're going to explore in the remainder of this talk. So step one, let's standardize an API to talk to these emulators and basically configure them for testing. So one of the important points that we want to emphasize here is that we should not be exposing any kind of implementation details about how the sensor represents a particular reading, right? We saw earlier that a lot of times these sensors will just have strange counts for how they represent temperatures and other readings. It could be in like weird units like 1/8 of a degree. We definitely don't want to have to be dealing with that. And so if we can basically make the emulator responsible for accepting a real-world value and it being the expert on the chip that it's emulating, map that into whatever it needs to do, then that would make the test side a lot easier. And finally, if we can add some kind of discoverability mechanism to the emulator, such that we can learn from the emulator what channels and what their respective ranges are, then we can really have a generic test coupled with this that's able to basically test the chip without knowing anything about it, only what it learns through the emulator. So I should mention that the concept of the backend emulator API is not completely new in Zephyr. There are some other classes of device that have been doing this. But I think it's particularly important that we bring this to the sensors world just because there's such a huge variety of sensors out there. There are dozens, probably over 100 drivers that are in use. And so I think that's a high impact area to deploy this. So let's dive into what this API actually looks like. And so this is going to be the point where I walk up to the screen and like point out some things, but unfortunately it's like 20 feet tall. So the main function is set channel, all right? So given a channel enum, and this could be something like ambient temp, XL, XYZ, there's a list of them in Zephyr if you want to take a look. So given a channel enum, set the particular value on an emulator, and then the emulator should do whatever it needs to do internally to make sure that the next read from that channel returns a given value. And then we also have the associated getSampleRange function, which is what we use for that discoverability mechanism. That's able to, if a channel is supported, basically return an upper and lower bound, so we know what to basically test with. And also an epsilon value, which sort of is like a tolerance. And that basically encodes the like bit depth or sample resolution of that sensor, just so that we're not trying to expect an output that's tighter than the sensor can actually provide, you know? We have since expanded this to also talk about sensor attributes, although this is still up and coming, so we're not going to focus on that too much, but just wanted to call that out in case you go look at the API, which is, by the way, in emulsensor.h if you want to follow along in the code. All right, so that takes care of the emulator side. Let's go on to the generic test. So I have a wonderful flowchart about how we can step through that process and how it can work. So first thing we need to do is detect if the emulator in question actually supports the backend API. If it doesn't, we're obviously just going to skip that. But if so, we can start that channel discovery routine where we're going to iterate through all the different channel types that Zephyr supports. And if we don't get an error code back from this function, we will basically store that channel information, the ranges, in a table inside the test. And from there, we can go ahead and interpolate some test values. So obviously, we're going to be using the absolute minimum and absolute maximum that the sensor supports. But then by default, we also pick a total of 5, so 3 additional points that are linearly interspersed along the sensor's range. That's configurable if you want to do something else. But we store those values, and then basically we can, one at a time, go through, set those on the emulator, and it will do whatever it needs to do to update its internal state, convert from a real-world SI unit. Everything in the generic test is using real-world units, such that when we read it back, we get that expected value returned from the sensor driver that we are testing. And then we can just do a simple comparison. Are we in tolerance or are we not? If not, we can abort the test at that point and return some information to the user. But if we do pass, then we can continue and keep doing this for the other sets of expected values. We basically will try to do every supported channel at once, and then repeat that for each of the 5 expected values, just to do a little bit in parallel. And then finally, we can repeat this for any other sensor that we want to. So I did want to go on a little bit of a side trip here and talk about fixed point numbers and the sensors v2 framework. So if you noticed in the API that we showed a couple slides ago, the values had a type Q31T. And there was this other parameter called shift associated with them. What does that mean? So this is a representation that is being used by the newer Sensors v2 API. If you haven't heard about this before, you're probably not alone. This is sort of an experimental slash soft launch feature that's been in the works. But we think it makes sense to start adopting this for new code, such as the generic test. And one of the things that we're doing in this new API is we're no longer using the sensor value struct, where it has 2 fields basically representing integer and then milliunits that you then have to basically add together and is very difficult to do arithmetic with. So we wanted to use fixed point numbers in a 32-bit container instead. And this makes a lot of the arithmetic easier in the processing with sensor data. The rest of the sensor v2 system basically plays more nicely with Zephyr's DSP systems and enables higher throughput reads through the real-time I/O technology. There is a slide at the very end that has a link to more information about this. I just wanted to quickly mention it because you might see some references to it in the rest of this talk. But aside from that, we're going to focus mostly on the fixed point numbers here. And so I'm sure you're all familiar with how counting in binary works. But in the fixed point case, basically what we're going to do is we're going to apply fractional weights to some of the bit positions in the number, right? So we're familiar with 2's complement that you can kind of see there on the left, but we can keep extending to negative powers of 2 on the right. And so basically we can start encoding fractional numbers in binary, and you don't need a floating point unit to work with this, so it's very friendly to smaller hardware. This is really common in the DSP space, so if there's any DSP engineers out there, you probably know all this by heart. What's one of the benefits of this is that we can actually adjust the precision of this by moving around where our virtual decimal point is. All right, so if you have a sensor that's spitting out really large numbers, you can sort of trade off some of those fractional bits to have more space or more headroom on the integer side. And the location of this decimal point is sort of defined by the shift value. This is a little bit different from the Q notation that you might be familiar with from the DSP world, but it sort of implies the same thing. On the next slide, I got a couple examples of what different shift values mean in terms of range. So you basically, every time you have one of these Q31 sensor values, it has to be accompanied by a shift value that communicates to whoever's consuming it where that decimal point lies and what the actual range of the number is. But this is flexible and allows you to basically get the best precision that works for your sensor. So a couple examples are out here on the board. Shift to 0 basically means that you have a -1 to just shy of 1 range to work with, all the way up to 31, in which case you have 0 fractional bits and it's just an int 32. So just to do a quick example, since being able to work with this is important if you want to use the backend API, if you had a temperature sensor that has a range of -10 to 100, what would be the appropriate shift value to use with that? Well, the answer would be 7, because that would give us a range of -128 to just shy of 128. That fits our range. That's the smallest shift that fits our range. So that's what we would use. And if you wanted to convert back and forth, there's a billion ways to represent this arithmetic, but you're basically just doing a rescaling. This one makes it very clear how the shift is incorporated. And that is how the temperature value of 50 degrees would look like in hex in memory. If there were decimal places to that number, you would see more bits being set in the lower significant bits. One thing to be mindful of when you're working with this is it is possible to overflow pretty quickly since you're dealing with some larger numbers here. So you might have to use an N64 container temporarily while you're doing the arithmetic. And you want to order your operations carefully to make sure that you don't have any rounding issues if you lose precision by doing too many divides, for example. But this will make more sense once you start working with this and can study some code. It is a little bit of a learning curve, but you will get used to it. All right, so for the last part, we're going to basically take a tour of a particular implementation. We'll take a look at the generic test as it lives right now. It is actually live within Zephyr right now, and there are about, I believe, 3 or maybe 4 sensors that are using this mechanism. We're going to take a look at the AKM09918C digital compass, because that's something we had on the dev board that was lying around. So that's been one of our sort of test sensors to work with. So first thing we're going to do is add a backend API implementation to the emulator for this part. And so as a prerequisite here, we're going to assume that we already do have an emulator for this part. That is something you have to set up first. But that's actually honestly not too challenging because a lot of these devices work pretty similarly under the hood. And so you can, with a little bit of copying and pasting, put something together in not too much time. But the first thing we're going to implement here is that getSampleRange function we talked about earlier. This is a pretty simple sensor. It supports the channels that we have laid out right here. It's a magnetometer, so 3-axis. Each axis has the exact same range. It's plus minus 49.12 Gs. And so that number means that we want to use a shift of 6, plus minus 64. So we're basically going to return shift of 6. We're going to compute the upper range based on that formula we looked at in the other slides. We can copy it over for lower. And then the epsilon, in this case, is basically based on the value of one least significant bit in the register of the chip. All right, so that's basically our precision. I recommend sometimes scaling it up by like 1.5 or so just to give you a little bit of headroom when there might be rounding errors in other parts of the code. But basically what we're saying here is that you're never going to see a step smaller than that figure. If the caller is requesting a channel that is not one of the 3 above, we basically return E not supported. We do not use the triplet samples. So there is a magnetometer XYZ single channel, but for simplicity, we just handle them each separately. All right, so let's take a look at the other function that we implement. This is the one that actually sets the channel. This is only half of it. So we just do some input validation to start off, make sure that we're only accepting values for channels that we support. So once again, we'll see the magnetometer X, Y, and Z. Otherwise, we return an error. And then we're basically just going to do some of that math in reverse so that we can convert that real-world SI unit number into whatever register representation this chip actually needs. And so as you can see below, we're basically going to convert this down to a 16-bit value that we can shove into our register store. All emulators have some concept of representing the registers that are on chip internally. In this case, there's just an array called reg, probably of size int 8. And we basically put the upper and lower half of the reading into it. One other thing that we have to do at this point is set the basically data ready bit at the top right there. This particular chip has a bit in a status register that gets set whenever a new reading is available. The driver will actually refuse to read any samples if that bit is not set. So we have to set it here. We are an emulator, so we have to behave like the real chip in order to make the driver work correctly. We're also clamping the value down just in case somebody sends in something that's way higher than the chip actually supports. We don't want to allow invalid register writes to take place, so we do a clamp. But long story short, you give this a value in Gs, or meters per second squared, I think, and it will do the right thing to make sure that the register gets set up accordingly. The last thing to do is basically to declare a backend API struct, give it references to both of those two functions, and then we register it in the emul dt_inst_define macro. So the generic emul struct that exists in Zephyr actually has a void pointer for a backend API already included. And you can set that with the last parameter in that macro, which is almost always null, because people haven't been using this before. But we'll take advantage of it. So that's all the work that we need to do over on the emulator side to basically get it ready for a generic test. So if you were adding this functionality to a new emulator, you could stop there, actually. The rest of this is just to talk about how the generic test itself is implemented so we can get familiar with how it operates. And so Generic test is live today, as I mentioned, and it's part of the sensor build all test. So this is a particular unit test that lives inside Zephyr that has a device tree associated with it that lists all the different sensors that Zephyr supports, categorized by what type of bus they're on. And so this is a really convenient place to start because it is the expectation that any new sensor driver gets registered here already. So we can basically use device tree macros to iterate through that list of sensors. And every time we reach one, we could basically declare a new z-test test function for that device. We get the device pointer automatically filled in, and we can call this run generic test function, which actually carries out the test. And we are repeating this for every single sensor that we know about. But the first check in the run generic test function is whether or not there is actually an emulator and the backend API associated with it. If it's not, then we're going to skip that test. Basically, it's hard to detect just from the device tree macros alone whether or not a sensor supports this. But this also provides some useful test collateral because you can basically see in your output all the tests on all the sensors that don't have support, so you can use that to kind of target which devices we want to work on. One of the other benefits of this build all test is actually now a run all test, I should say. Since we actually are initializing Zephyr, it will go through and run the init function at least on all of these drivers, which will at least test the initialization function of each driver, which does help a little bit. Sometimes that catches bugs on its own, but we are going past simply building, despite what the name implies. All right, so going a little bit further down in the generic test function, we're going to do that channel discovery routine that we mentioned earlier. So iterate through all the known channels. We're going to keep track of which ones the sensor emulator is actually able to support. We build out a table of channels and ranges. And then the final step that we do at the bottom right there is do that interpolation. So we create a set of test values that we can work with. And once we have those, we can start setting them on the emulator. So the key function here is emul sensor backend set channel. That calls into that API that we defined earlier. We give it the value. We give it the channel. Emulator goes off and does the right thing. We will then go ahead and read those values back from the driver, which is then, of course, talking through the emulator. And we capture all of those into our table. And then we can finally do a comparison at the end to make sure that we got back what we expected. So the first thing that we're actually going to do in this case is unshift everything. So one of the consequences of fixed point numbers is that if your decimal point is actually not in the same spot between two numbers, you cannot directly compare those or do arithmetic on them because the bits mean different things. So we basically just take that whole problem out by unshifting everything. It fills an N64 container in this case, but that doesn't matter. We're running on PCs here. That's actually the native size. So once we've unshifted the actual, the expected, and the allowed error, the epsilon value, we just use the z-assert within macro right here to see if we are in tolerance. If not, we can report an error to the user. Otherwise, we can just continue in the loop, testing all the other sets of values, and eventually moving on to other sensors. All right, so in conclusion, if you can write a backend API plus emulator for a sensor, you basically get a free test. Obviously, this will not be able to test every single feature of your sensor driver, but it does cover the data path, which I think is one of the most important things to focus on. And you can always still write a dedicated unit test for that sensor on the side where you work sensor-specific features. And so my ask for you guys today is that if there is a particular sensor in Zephyr that is important to your product or project, consider taking some time out of your day to contribute an emulator and backend API implementation for it. It does not actually take as much time as you may be fearing. I would estimate maybe like half to 1 day if you are generally well versed with Zephyr. And even if you think you've got a perfect driver that you wrote, you never know, it could be somebody else's PR down the road that introduces a regression into it. And if there's not testing going on to catch situations like that, then that is the vulnerability that we don't want to accidentally have happen. But the best recommendation I have would be to try to, every time you develop a new driver for a sensor, do the emulator alongside while it's fresh in your head. That's kind of the easiest time to just crank that out. So as promised, at the end I have a couple of references. So these are all various PRs that are associated with the generic test and the backend emulator API project. At the very bottom here is a reference to another talk from last year's conference about the sensors v2 thing, if you want to learn a little bit more about that. Yeah, so feel free to take a picture or download the slides from the web. I'll leave that up for a little bit longer, but aside from that, we can go ahead and enter the Q&A session. So yeah, do we have any questions from the audience?
Thank you. Does the emulator backend have an interrupt emulator as well, so you can do things like triggering and that kind of stuff? Or just registers on the I2C bus or that kind of thing?
Yeah, so right now it's just register-based one-off reads. But since we are tying into the the sensor v2 API right here, that does open up possibilities for that kind of asynchronous sensor reads that are often triggered by interrupts. So I think there's potential to work on that there. Okay. If it's like really particular to a certain sensor, then that might be a case where you do need to, unfortunately, write a dedicated unit test for that driver, though.
Okay, thanks. Also, I hadn't seen sensors v2 before. Is there a reason that the 32-bit and the 8-bit are separate and not in a structure like they were for v1 with the integer and fraction? Or is it just they decided to do it that way because they decided to do it that way?
Yeah, so the main benefit of having the single fixed point value is that arithmetic gets a lot easier. So you can actually add, as long as the shift value is identical, you can actually add and subtract those together and do multiplication on them. The previous implementation where you had the sensor value struct, where it had basically two numbers in one, made that pretty complicated because basically the first thing everybody would do would be to somehow recombine those two values. Yeah, so they would multiply, the first number by 1,000,000, then add the micro units into it or something like that, which could overflow or maybe isn't actually suitable for the application. So there is, of course, more of a learning curve to the Q31 numbers, but I do think it's possible to get used to it, and I think it's an overall improvement.
Oh, no, I understand that. I was just wondering why the 32 and the 8 are two separate things being passed in and out rather than just
okay. So you're saying could those be within one struct?
Yeah.
I'm sure they could be.
Just wondered if there was a reason that it was done that way, that's all.
It might be for compatibility with the DSP layer.
Yes, so Keith's comments is it might be for compatibility with the DSP layer. Yeah, I think a lot of this was designed with that in mind, so that could definitely be the explanation.
Okay, that makes sense. Thank you.
Just a note on that question, it could possibly be due to array support. If you have an array of 16 samples, you don't need the shift value repeated 16 times.
Yeah, so you're saying whether or not you could have a whole buffer of samples that are described by one shift parameter? Yeah, so actually in the Sensors v2 system, when you are doing like larger batched reads, the shift value is only sent once, and then you'll have a whole buffer of samples. For the emulator API right now, we're really only supporting just one-off samples, so this is just a simpler way to do it. But I definitely do see potential to expand this in the future to basically set up like maybe a whole waveform on the emulator so that when you do multiple reads in a row, it just returns one after another, and then you could use that to characterize a filter or something like that.
Thank you for the presentation. Well, one of the things you mentioned before actually explaining how the emulator worked and stuff was about a bug that, for instance, you have a driver or a sensor that it's working over I2C, that it's not working over SPI. So kind of like, I'm curious, how would this emulator detect those kind of problems?
Yeah, so that one was actually caught when we turned the build all test into a run all test. Because then it started initializing all those sensors, and that's when we started seeing some problems with some of them. So in that case, there was not an emulator involved, but it did shine some more light on and run some more code than we had been in the past.
Any other questions for Tristan?
Thank you. So I kept thinking about that epsilon and patting it a little bit, and I was wondering if you considered in the emulator API to get back not only the epsilon, but maybe Q31 type that the API will calculate as this is what I should have after losing precision, and use that as well for the exact comparison, not to get into well, actually use them together with epsilon as a double check, because that last bit sometimes can be important, because if the driver is truncating the last bit, that is actually noise. So I was wondering if that could be an option.
Yeah, that's a good point. So basically saying pre-compute what the actual value should be, just so that if there are regressions along the path that maybe even minorly affect the accuracy, that those can get caught?
Yes.
Yeah, I think that's a good idea, actually.
Okay, thank you.
All right, any final questions? All right, well, thank you so much for attending. It was nice talking with all of you. And hopefully I can review some drivers and emulators from you guys. Hopefully I can review this.
Check, check. Check, check. Check, check.
Hello, everyone. So this is Meet the Maintainer session. If you are a maintainer in Zephyr, please join us here at the front so you can speak up and answer questions, if need be. This is something that we started doing just last year, and it was really good, really successful. Yeah, and yeah, but Kate is not here. Yeah. No. Yeah. Yeah. So, so we have people here, and non-maintainers, please come closer so you can actually participate in the conversation and ask questions without us like being spread around. Yeah. So does anybody know if Kate is coming? She is, okay. So again, as I said earlier, we did it for the first time last year, and it was really interactive and very successful. And a few actually of the points that were raised by the community and the various maintainers were taken into consideration. We had like a lot of actions and a lot of things that we did to improve our overall, processes, guidelines, and moving things forward. So basically, I would start like with the few or the major problems that we as a community had, and we started to address, and that's like really the interface that we all have, which is GitHub, yeah, where we all meet, where we all converse and push our code and try to get reviews and try to get our changes and features we are interested in into the project. And one of the major problems that we had is like, one thing is the review time, not getting reviews, or getting the wrong reviews, and things sometimes not being merged in time, although there are reviews, or things that are merged very fast, and so on and so on. There's also a few issues that we talked about also in the TSC meeting that we had this week. About how do we actually go from somebody having an idea all the way to introducing this, into introducing something like that into the Zephyr tree. The RFC process, how do I propose something? How do I get feedback on an idea or a feature? And how do I drive something like that through the project? And it seems like based on the conversation that we had and based on a lot of the experience and a lot of the interactions with developers and the community, it seems like this is not really understood and not perfect, and something that we definitely want to improve, so nobody's time is wasted. And that things actually take the right path very early on, instead of creating conflicts sometimes, and as I said, wasting people time in terms of introducing new features. So this is like one of the things that we definitely need to talk about and get your feedback to be able to address. One thing that we addressed based on the feedback from last year was what we call right now the 4I principle, which is basically making sure that code changes get proper reviews from different stakeholders in the project, and that features don't get pushed, reviewed, merged, submitted, everything you want by one single organization. Yeah. That's something that we established based on the feedback that we got here. And I think it's working really well right now, yeah, in terms of like making sure that people are reviewing the changes and the right way, and that things don't get rushed into the tree based on one organization preferences or schedules and stuff like that. So there is always another set of eyes that looks at the changes and at least make sure that they are neutral and they are, sane, from a project perspective. And that actually is now documented. We need to find a way how to track it, but it's actually going really well. So these are like the two things that decision making, that we definitely something that we want to improve. And I just talked about the review process, the 4I principle which we introduced, and it has been working really well. I wonder if others have any other items they want to put forward, things that need to be discussed, that can be positive, can be negative as well. Yeah, don't hesitate to put also tough questions to the maintainers. We don't want to get into a review process here in this meeting in terms of like specific PRs and stuff like that. Usually this will not be productive, yeah, but try to help us as a community and try to get things moving forward for everyone, yeah, and not individual requests related to individual areas. So with that, I would pass the microphone to some of the maintainers here, just to give like, their thoughts about how things have been going, and then give the floor also to the community here to raise their concerns or their feedback in general. Yeah, Brix, anything you wanted to add? No.
Sure. Yeah, so I think overall, I mean, Zephyr seems to be a growing, flourishing community. The thing I would say that's, from as maybe a maintainer is I do think, Zephyr has a lot of users and a relatively small group of contributors in most areas, right? Like a lot of the chip vendors, or in this case, Brix, right, for CAN, for all chips. But, I would say just don't be afraid to contribute back. Even small things are very welcome. I think we try to be very welcome as a community. And really, that help is greatly appreciated. So, yeah.
Yeah, I'll just, adding on to what Anas is saying, we're trying to be transparent with everything that we do. Even from, the governing board perspective, we've got certain objectives that we want to improve on the project and to push down to the TSC and then push down into our community. And we look for the feedback from the community. The honest, it was a focus for since the surveys came back, multiple meetings looking at it. Benjamin processed the data through ChatGPT, I think, to try to figure out what the trends were that were coming back. Because as individuals, we all have, most of us all have day jobs and stuff, and we're trying to either, push along our own company's interests as far as enablement and stuff, but we're pretty much all of us are very cognizant to the fact that in order for the Zephyr project to continue to grow and to be successful, it has to be open, and it has to be, we as maintainers and stuff have to be aware of where the pain points are and then try to figure out ways to address them. And so we do, actively look for that feedback from you guys.
Anyone else before we pass?
So since we're talking about maintainership and maintainers, in general, aside from the eternal not enough maintainers problem that I don't think we need to go over because we know there's not that much we can do other than attracting talent. I think one of the things I'd like to discuss that we have a problem with in this project is big changes. So it's really hard, and I understand that might be the case in other projects, I don't know, but there are proposals of changes that are bigger in size, in context, that are really hard to push through. And I think maybe we can do something about that in the sense establishing timelines. There is something, already some precedents in our documentation, but perhaps if something is presented, it's well described, it's justified, and there is no reason for it not to progress, even if those that have objected to it disappear, there has to be a way to move it forward. And I think that's one of the things that I've been seeing as part of the architecture working group where many maintainers attend, is this difficulty on pushing bigger changes because of concerns and backwards compatibility. And I think there is something we can do there, not, something in terms of agreeing together how best to do this without, obviously, without putting at risk the integrity of the project. But there's been too much frustration in the past with this kind of, from many people, not only, obviously, particular maintainers, in general, about the inability to do this. So that's one topic that I think is worth discussing. Okay, there's another one.
Yeah, I'm probably the worst person to make points about process, but since it is a sort of a maintainer-focused issue, and we seem to be on the opposite side of it here, has anybody given any thought to the XZ debacle and the fallout thereof? I mean, there have been, so the circumstance there obviously was that you have a project with not enough maintainers. In that case, the number was 1. And someone shows up and is helpful and great and achieves, commit rights and, proceeds to then backdoor the project. Zephyr isn't susceptible. Like I say, I'm not really the right person to talk about this, but I do think it needs to be mentioned. Maybe this is more of a TSC question. But we're not as susceptible simply because we're not a single project. A backdoor in Zephyr is kind of a nebulous idea. But there have been, I'm not going to point any fingers. There have been sort of two moments in the last couple of months where I kind of thought maybe there was something in progress kind of like that. Like there was a commit that showed up from a, otherwise minor contributor, and they had a bunch of warning fix-ups, and I kind of pointed out that like one of them involved a whole class of casts where you were taking what had been a arbitrarily typed thing, and you're casting it down to a 16-bit value, and I forget all the details, but like that can have security impact if you're actually truncating the top half of the word. And the other one was a request to add someone as a collaborator, and a collaborator's not like a big deal, right? But it was I think it was Chris that mentioned that it was a person with only 5 commits, and and I don't want to, there is zero real suspicion here in any way, and I don't actually think anyone's trying to backdoor Zephyr. But is this something we need to talk about as a process kind of thing, or at least to give some?
Yeah. Yeah, I've been given this actually particular thought mainly because of part of my background from a previous life. That particular instance, you have to look at it as a long con, right? So the person coming in with just a couple of commits, you can look at it, and you see the changes, but these entities that are going to do those kind of things, this last one was found because they had a bug, right? And every software has bugs, and those entities that are doing those kind of things are usually going to be focusing on that really hard. And also, you're particularly exposed because they were binaries, right? You're not going to see that. But I do think it is something, the project, and I was planning on bringing it up internally with either the security, probably in the security one, just to start it there. Let's think about this. What is it that we would do potentially to be aware or to look out for something like that? I think in this particular case, you've got a contributor that nobody really knows, right? It's just a name, right? Does anyone even have a face for this person? No, I know that, but I think it's something that you, as a large project that is being used and growing, you do want to be, I think you do want to have some sort of a, not necessarily a position, but to start, building into your processes things that would.
Right, like name brand employer, years long history, that sort of thing. But again, I have no suspicion of this individual at all. And the request was just for collaborator status, which is literally just so you can @ them in a GitHub issue, so that to ask for a review. I don't think that's a problem. It tickled my brain enough to think that I think we might want to give this some thought.
Go ahead, Kumar.
Just as you're thinking about it, David, I think looking at, and I forget the history here with what the Linux kernel did with regards to like key signing and so forth, so that way commits, and not to say that we need to go to that degree, but something like around maintainers, where like some of that model where you had to have somebody else sign your key and so forth, so that at least there was someone was real, right, to some degree at some point in, again, not to say that's at the contributor level, but maybe as you get to a maintainer level or something, to that long con potential concern. So,
yeah, I think I know what Andy is referring to exactly. Yeah, and by the way, that's really funny, because when I went through the history of the exploit in XZ. And looked at the names of these guys, somehow that correlated. Probably Andy knows what I'm talking about. And I thought about it multiple times. Yeah, the social pressure and the social engineering, and how do you get commit rights, and so on and so on. But I mean, obviously, we the way we are running our project is different from how these projects are run. But I think the problem, and that's something that needs to be discussed, is that we have, and Carlos pointed that out, we have a problem of, maintainers, yeah? But more than that, we have problem of, to get to a maintainer, at least per our process, you have to be a collaborator, right? So, and people who actually review stuff, yeah? And the way we are doing things right now is that we used to have the code owners file, where would people actually get notified when something has changed. Right now we have the maintainer file, which does that exactly. And certain people want to get notified when something changes, maybe because they care about this, and that's really great, yeah. And there is the other side of things from people, from vendors in this instance, who are very active in the project, but they are hesitating to actually go and add themselves into the maintainer file, maybe because of how we are documenting things and how we are like. It seems like it's almost, we are telling people, okay, we have this concept of maintainer, collaborator, contributor, etc.